Testing, testing. And then Chris is going to come up for luminaires. And then we're going to do just kind of the final review recap of all 9 previous modules. Any questions about today or the structure? Okay. I think we can go ahead and get into it.
Cool. Excellent.
Take it away.
Thank you, Brian. Does anyone have any like time constraints today or hard cutoffs or anything that we need to be wary of? Bless you. Cool. Okay. Now some folks on the IES side might have to dip out a little bit early, but sounds like we're all in it for all in it together as usual. So happy Saturday. Thank you for making the trek. Welcome to Module 5, Lighting Controls. Halfway through. Let's get going here. Boilerplate. Does anyone have any questions on like the getting your course certificate or anything like that? Any of those housekeeping items? All pretty straightforward, I think. I know Brian's been doing a good job of communicating about that, so. Cool. As we're going through this, if any questions, thoughts, comments, conversation topics come up, please just blurt them out, interrupt. This is for you to learn all this stuff, of course. So, lighting controls, learning objectives. This is what we're going to be looking at here for the next hour and a half or so. And I want to point out that if you are kind of newer to lighting and controls, the first and the last bullet points are where you're really going to want to start with this control stuff. There's a lot to it. You know, it's not rocket science, but there's definitely a lot of layers, a lot of details, a lot of nuances to this whole domain. And kind of before you dive in and try to figure out, you know, wireless protocols versus, you know, digital networking and all that sort of stuff, it helps just to kind of have that base level vocabulary, confidence to be able to kind of talk about lighting controls. So focus on that particularly as we're going through. And then also just kind of focus on why lighting controls are out there. You know, what's the point? What's the purpose? Those sorts of things. And that'll be kind of a good foundation for you to focus on here. If you already are a little familiar with lighting controls, you've been designing, you know a thing or two, well, great. We get into the weeds a little bit on technologies and sensor different technologies. So a little bit for everybody, hopefully here today. Speaking of vocab, let's look at some of these. So if you look at this list, you probably, know what some of these are, what a lot of them are. Maybe you know what all of these things are, but we're going to talk through. If it's showing up okay, I have some that are kind of bolded and italicized. We're going to talk through those real fast. So astronomical time clock. Who knows what that means? Brittany?
It's a clock.
Nice. Yep. The astronomical component, what does that mean to you? Longitude and latitude, perhaps? Yep. Exactly. So time clock tells you the time of day. Astronomical, that tells you where you're on the planet, and thus when the sun rises, when the sun sets. So that allows you to do dusk to dawn, overnight sorts of operations like that. Excellent. Thank you, Brittany. Controls intent narrative. This is something that gets published by the engineer, by the lighting designer, by the control specifier in the documents. And that tells you, how is this room going to operate? How are the lights going to turn on? What do we need the lights to do? Controls intent. That's a very important term for designing, just understanding what these things are actually doing. ELV, who knows what that means? Madison? Yeah, nailed it. Tell us more about that. It is a dim type. Electronic low voltage, we'll get into that. There's a slide for that. Yep. Yeah. Celeb shot real fast. Just kidding, Crystal get here for sure. Yes, electronic low voltage. It is a dimming technology, a dimming protocol, if you will. we'll get into that. Gateway / head end. Anyone have an idea what that is? Princess? One of these guys, yep. A brain. Usually a time clock is in there. Usually some connections to the rest of the system, maybe some internet connections, that sort of stuff. But yep, gateways, when you have them, the brain of the system, right? Load, that's what we're controlling. So this light is a load. This plug load is another load. Plug load power pack, lighting power pack, UL 924 in this case. So load, it's just the thing that we're controlling. Network is a big term. Maybe you've heard it before. And it's barest term. What's that? Exactly. Yep. Network is devices exchanging communication between them. That sensor is talking to the brain, which is talking to the switch on the end, communicating back and forth. Nothing too crazy. PIR, passive infrared. It's how sensors see you move into the space, turn the lights on, or you're not there, they turn the lights off. Phase control. It's an overall umbrella term. ELV is a type of phase control. Who can name another type of phase control? It's similar but different. That's a dimming technology. Phase specifically. Ian? Triac, that's very good. Yep. Yeah, triac is kind of synonymous with MLV, magnetic low voltage. So that is, yeah, the other one. ELV, MLV. Forward phase, reverse phase, et cetera, et cetera. Riser diagrams. Self-explanatory, maybe. It's another thing that the engineer, that the specifier publishes in their documents optionally to illustrate the system, illustrate the network backbone, illustrate the parts and pieces of that lighting control system. A scene. It's kind of like a setting of lights, right? So, you know, dim your zone A down to 50%, zone B 100%, save that. That's a scene. Then you can recall that at any time. Sequence of ops, or like a lighting control matrix, lighting control narrative. That is kind of synonymous with the controls intent narrative over here, right? So again, very critical to publish that information so that everybody knows how the heck these things are supposed to operate, what they're supposed to do. There's occupancy mode. Who knows what vacancy mode is? CT? Very close, yep. Yep, so there's occupancy modes. It's one of these aux sensors. It can be either an occupancy mode, which is where you walk into the space, it sees you, turns the lights on automatically. It'll turn them off 20 minutes later or so. Vacancy mode, you walk into the space, nothing happens. So you have to manually turn the lights on, and then once it's vacant, 20 minutes later, it'll turn the lights off. Yep, so that occupancy versus vacancy mode, really that tells you how the lights turn on in the first place. Finally, zone. Yes. We can. Yep. Okay, cool. Yep, we'll get into that on the energy code slide. Zone. Pardon. Yep, pretty much. Yep, so a zone can be a group of lights that's controlled together. Yep, so these ones could be zone A, zone B, zone C. That you can map each of those to an individual switch or a button. A, on off, B, on off, raise lower, C, et cetera, et cetera. Then you can combine different settings of zones into a scene or a preset. Excellent. Any other words on this list here that anybody is curious about? There's a lot going on. Happy to spend some time here. Just shout it out if you're curious.
Are we going to move into phase control?
We will. Yep. Yep. Who here knows what an RF node is? Just a wireless node, communication node, a module. Stick it on a fixture, make it a smart fixture, et cetera, et cetera. Anything else? Wonderful. Let's dive on in then. Brief history of lighting controls here. If you can see this okay, that's coming in pretty well. The PIR sensors invented way back in the day. Solid state dimmers, that's basically MLV type dimming, magnetic low voltage forward phase, triac, if you will. Triac is the name of the actual physical device, the little like electronic device that is doing forward phase dimming. So triac is the actual physical thing in there. Those came out like 1962. ELV dimming, reverse phase, came out 80s, something like that. And that was in response to kind of low voltage MR16 type track lighting, where it needed a kind of a different twist on that dimming technology to perform a little bit better. So that's what you see going on here. And then time goes on, technology expands, you know, Dolly comes out, wireless controls become a thing, et cetera, et cetera. So here we are in 2025, it's the future, all sorts of cool stuff going on out there. So why lighting controls? Why do we have to design them, think about them, burden owners with lighting controls? It's several reasons, of course. One we're probably all most familiar with is energy code. We have to. They're legally required in new construction for the most part, based on your jurisdiction. So why else do we do this? Saves energy. It's a good, responsible thing to do. Turn the lights off when nobody's there. Provide dimming, you know, make sure it's the right quantity of light for the situation and not something, you know, obnoxiously bright. Way too much light in here, in my own opinion. So lighting designers have all good intentions with selecting lumen packages, you do running photometrics, all that sort of stuff. But once the lights are actually into space, you don't really know what you're going to get. So it's nice to have maybe some dimmability there to go with your new lighting system. Okay. All right, so we have to, it's legally required. It pays to. We looked at that ROI calculation Thursday evening. You know, dimming this down, we're saving real watts right now. We're saving pennies throughout the day. Across an entire building, across an entire tower, across an entire campus, those savings add up. And we're also going to see we can interface to other systems, HVAC systems, that sort of thing, and reap even more energy savings. You know, sending the occupancy status to the local VAV or to the local HVAC controller allows us to turn the HVAC off also. You know, saving LED electricity is great. Saving fans and pumps and heating adds up that much more. So a lot of real savings here that lighting controls can bring. And finally, you know, there's a lot of fun stuff that we can do with these lighting controls. Oh, wait, that slide's coming up. So lots of good reasons to do it. And you have to also. So better to just kind of lean into it, get familiar with what lighting controls are all about. Yeah, keep building on the knowledge base there. So have to. Energy code compliance, IECC, ASHRAE that we talked about the other day. Those are the main drivers for why these lighting control systems are here. You know, it's sensors and those time clocks, those are what provide the automatic shutoff that energy code is really looking for at the end of the day. So energy code really driving a lot of this stuff in the first place. Pays to, we talked about this a little bit. You know, turning the lights off after 20 minutes, great. Turning the light off after 10 minutes in the right situations, even better. If you're an engineer or a specifier, you're able to dictate that timeout in your sequence of ops, in your controls narrative. So if you're in that place, you can start thinking about all of these requirements. How do you articulate them on plans? That's what your matrix, that's what your plans, that's what your layouts obviously are there for. Want to. So there's a lot of fun stuff that we can do with lights and controls. Let's see if I can do this. So if we all look up at these lovely things, does anyone notice what's going on here a little bit? Sure. Yeah, exactly. That's kind of fun. We are invoking curiosity. We are invoking interest right now. Let's try something else here. And I apologize in advance. Disgust, discomfort, it's so bright. But what's going on here? This is fun. Get back to it. Just keep mashing buttons here. Let's try these other buttons. This thing about lighting controls is that trying to make them intuitive and really cool, it's a tough balance. But this is pretty fun stuff, right? Interest, delight. So it's my feelings every day of life. Boy, that's really bright. Turn that back down. We'll leave our Broncos scene alive and well. So, all sorts of fun stuff that we can do with our lighting controls. Make the space more effective, make the space more flexible depending on what's going on. Invoke emotion. Lighting controls in the theater, of course, are a whole big deal. And you can imagine just the importance and the significance of those productions that the lighting and the controls play. So lots going on with the controls, hence why we're talking about it here. So this is really good information to how to think about lighting controls from the start of a project to the end of a project. There's both the written design process, but before that, you actually have to know like how to think about this stuff, how to approach this stuff. And this does a really good job of kind of stepping you through that mental thought process. So what that kind of looks like is ask yourself, what lights are we controlling? That's zoning. We're controlling zone A, we're controlling zone B. What lights are we controlling and what do we want them to do? Turn on automatically when someone walks in the door. That's occupancy mode. That's only allowed by code in certain spaces. Code typically says you need vacancy mode where you have sensors. So private offices, conference rooms, break rooms, classrooms, spaces like that are required in code to be that vacancy mode, right? So you have to turn the lights on. They will turn off automatically after you. But other spaces, restrooms, corridors, lobbies, more public spaces, those are allowed to be in that occupancy mode. Just automatic on, automatic off, keep it easy. Do you want the lights to dim? Do you want them to change color? When do you want them to do that? Do you want, business hours operation to be different than after hours operation? You have a lot of options and you're able to articulate those if you have the right tools and the right drawing standards to start, getting this stuff, communicating this stuff to the project. How do you want to control the lights? Manual mode, automatic mode, combination of both, time of day. And then finally, this is when we start pulling it all together into a system. How do you want to connect the lights and the controls and the user together? Is there a relay panel back in the electrical room that's turning the lights on and off? Are there power packs with dimming outputs going on? Are there fixture-based, individually addressable fixtures talking to each other wirelessly, talking to each other over Cat5, over 2-wire, you know? So once you go through this process, really that final step is only then is when you really start getting to like the parts and the pieces and the system level of stuff. But you have to have an idea of what you want the lights to do, what we're controlling, what it's doing, then you put a system to it. Make sense? Questions? Beautiful. Quick example here. So we've got the space. Turn my laser pointer on. There we go. So, bunch of lights. We have some 2x2s. These are zone A. So we're identifying which lights we want to control. We have zone B is these 2x4s in the middle. We have switches over here and over here. The switches are right here, that little DA. We're dimming zone A over here and over here. We're dimming zone B here and here. And then pulling in that sequence of operations that controls intent. So up in this matrix here, this little LC13 tag, lighting control tag, if you will. Slap that right there. That gives us enhanced information about what's going on. So manual on, automatic off. That's vacancy mode right there. We have dimming. We have sensors, dual tech on the ceiling, turns off after 20 minutes. Some additional features over here. We want to connect this to a network. We want to connect it to a brain, is what that means. That gives you time clock. That gives you the ability to program from the laptop from a single point. What else is going on? We also have emergency lighting here. So just a quick little snapshot of what a plan and what that control matrix, put those together, what that tells you, how that articulates your controls design. Questions, thoughts? Excellent. Okay. Circle back again, hit some of those vocab words again. Load, it's what you're controlling. It's the lights, it's the plugs. Zone, loads you control together. So all these lights are in a zone, all those lights are in a different zone. Scene, it's a setting of lights. Bronco scene. Excellent. So who's involved in lighting control design? There's a lot of players, as with most things in the industry. Your lighting designer, of course, will be involved. They're picking those lights. Those lights tell you the dimming protocols, tell you the connection protocols, the voltages, all that sort of stuff. Lighting designer should be helping if there is a specific lighting designer on the project. They should be helping with the zoning, defining the zones to help really articulate the lighting intent. Electrical engineer will be involved. Somebody has to be that lighting control specifier. Usually it's either the engineer or the lighting designer. And very often it's the engineer. Sometimes all three of those are the same person also. Lighting controls integrator, who's programming the lights. That term integrator, that is kind of specific for, fancier high-end DMX and color changing, rock shows, theatrical entertainment type stuff. Those types of projects will typically have that person, system integrator, who they're just professionals at programming and tying, complex systems together like that. The manufacturer's rep and the system vendor will be involved as well, just to really get all the details, tell you the exact part numbers, get those submittals put together, and put the finishing touches, make essentially take where the specifier and the engineer left off, produce the shop drawings, produce the product data to make an actual constructible design. Take it that final step. Then all of these folks over here are often involved as well. IT manager. Who knows why an IT manager might be involved with lighting controls? Network. Yep. This thing right here. I've got some internet ports my laptop is actually plugged into right now. Generally, that internet connection is optional on these systems, so that networking term doesn't necessarily mean connected to the internet, so there is the lighting control network, which is essentially this daisy chain here going off to those devices. So in a lighting controls network, that's the typical definition we're talking about. But networking is a big term, so there are all these additional layers too. So yes, if we're connecting to the client's, building LAN, building Ethernets, that's when the IT manager gets involved. They usually tell you which ports, your IP addresses, all of that sort of fun stuff right there comes from the IT department. Questions on this slide? Who here is a lighting designer?
Thanks.
You wear a lot of hats, a lot of different roles. Electrical engineer. Specifier. You're all of you people. Reps. Excellent. Is anyone actual? We have some architectural backgrounds. Is everyone a practicing architect right now? Takes a village. All righty, getting in there now. Dimming. It's for the nerds out there. Phase control. So back in the day, incandescent lamps, halogens, forward phase, MLV, magnetic low voltage dimming. What is that exactly? And so picture your sine wave, right? Your AC 60 hertz sine wave. MLV or forward phase dimming chops off the first part of that sine wave. You're coming along, it sees the zero cross right here, where you go from positive to negative, and the triac, the actual device, just shuts down for part of that cycle, and it does that repeatedly. So that's less current getting to the light, that's less light out of the fixture, is how this works. So you dim a little bit, you're just chopping a little bit of the wave off. You dim a lot, you're chopping a lot more of that wave off. So this is how, like, just standard dimming at your house, incandescent dimming, this is what's going on. And this still exists today. Some LEDs with the right compatible drivers, with the right components, can accept MLV dimming, this forward phase dimming. So it's been around the longest. It's probably not going anywhere. It's cheap. It worked a lot better with incandescents, but LEDs with the right compatible stuff can do this as well. Now let's flip it around. ELV, reverse phase, trailing edge dimming. These are all just synonyms for the same thing. You got your sine wave. Now you're chopping the tail end off. And the reason you would do this as opposed to that forward phase dimming is because this, as the current comes through, you chop the first end off. This is a real big spike, a wall of current, essentially smashing into your light, smashing into your components. And that can cause a pretty big, like this voltage jump causes a pretty big current jump that, like, the delicate electronics and LEDs and some of the low voltage lighting in the past did not handle this wall of current crashing into it 120 times a second. So ELV was introduced. It's smoother. It's that steady, you hit the zero, rise steadily, and then it chops off the tail end. And the device that's doing that, it's basically running, it has a quick little timer going on. So the device sees that zero cross, and then it is calculating the time until it needs to turn off. So same thing, you just chop more of the wave off, the dimmer you want the lights. Because it requires more parts, this ELV, as opposed to MLV, little bit more expensive, not as high of power ratings on these types of devices. But ELV dimming, we see it a lot presently with more decorative type LED fixtures, a lot of legacy control systems in the theater, that sort of stuff, still operate on ELV dimming, MLV or ELV. Questions on phase dimming? It's chopping that sine wave. Another thing to point out real fast, this is, you can also call it line voltage dimming, mains dimming. There's a lot of different terms for these. And this is all happening on your line voltage in your neutral, right? So it's just dimming over the power lines, over those two wires. And that's different than 0 to 10 volt that we're going to see here in a second. Don't need to talk about that. Don't need to talk about that. Yes. Not the only reason. The why we move from incandescent to LED. The energy savings for the most part. But yes, the dimming technology had to keep up because now that we had LEDs, that traditional dimming didn't work very well. You know, to make the point real fast, the LEDs themselves, the diodes, the little tiny things, those are inherently dimmable. You know, just that little product, absolutely nothing wrong. It just, you know, a fairly proportional amount of light that it spits out compared to the current that's coming in. However, with the LEDs come drivers and additional components. Since those drivers, that's where you really need to focus the question of compatibility and, you know, what dimming protocol are we using? That really boils down to the driver. That's the key components in the system here. So making sure that your driver and your dimmer are compatible. Chris Slaughter.
All right. LEDs, student, my voice are already knowing, they have no internal resistance. So you can technically throw however much current you want to that thing, and it will just go poof, and very light will go poof. So that will happen if you don't control the current going through the LED, and that's the main driver, just control the current going through the LEDs. So that's why we needed kind of a different technology. So LEDs work on inductance, not resistance. That kind of changes.
Interesting. I learned something. Thanks, Chris.
Welcome.
It's very interesting. All right, 0 to 10 volt dimming. Now we're getting a little bit different here. 0 to 10 volt is an analog signal between 0 and 10 volts, and it operates over dedicated 0 to 10 volt wiring. So let's see this one here. This is a power pack. This is a power pack. These are the 0 to 10 volts leads coming out of that power pack. So we have your line voltage, your hot and your neutral coming in. We have a relay in here. And if we're quiet, can you guys hear that clicking? Relay opening and closing. Could you actually hear that back there? Yep. A mechanical relay, open, close. A relay is just a switch. In addition is your dimming wires. So essentially a 4-wire system now, sending your analog 0 to 10 volts over the violet, and the standard is now pink. It should be a violet and a pink wire. The old standard was this violet and gray. You know, it's kind of hard to see. But this is the actual 0 to 10 volt signal going between the fixture driver and the power pack, the 0 to 10 volts sync side over here. And just a nice little resistance-based circuit. The voltage that you manipulate the resistance on the power pack side, and that changes the amount of current flowing to the LED to the fixture side.
Controls or systems that are set up where a driver controls multiple fixtures. So like for a room, you have a single driver that is plugged into the switch dimming controls and then extends out to your fixture.
Yes, there kind of are. And the driver itself can be packaged in a bunch of different ways. You could have a driver cabinet where you know, consolidate all of the actual LEDs on the ceiling, run them back to a single driver cabinet. And you might have different like driver modules in there. Another thing is, strip light or tape light. That's what's the watts per foot, wattage required per foot. And then you kind of pair an associated driver with that. But it's really kind of like a manufacturing a luminaire componentry question. But yes, you can have multiple things from a single driver.
Is there?
There are, yep. And that kind of varies based on the product, but it's just the voltage drop. Just normal like circuits and normal physics are what is limiting that. They're typically in the same room. Yep. And Chris might have some more information on this too. But Chris, driving multiple fixtures from a single driver. Do you have thoughts, comments? Yeah.
Oh. It's not super standard. What's more standard is you might have like a driver with 2 or 4 outputs. Perfect example of that's like an RGBW driver. It's like 4 outputs, and you would control like red, green, blue, white independently. And that would have like 4 different channels of output. And then you can think of that as well. They don't have to be red, green, blue, white. It just be white, like white, white. Another example is in tunable light. You typically will have a driver with 2 outputs. You control the warm white LEDs and the cool white LEDs. So that you can think of that as like 2 luminaires in the same box, right? It really depends on how you think about it. Yeah, that's integrated mixture, but all it is really wires going LED boards at the end of the day. So you can have that driver outside, and PoE does that, like low voltage drivers do that. The Acuity DC to DC system of that, like you can totally drive the same box. Just about how you hook up the wires and what those wires do. And like I said, many drivers have multi-channel.
Nice. So 0 to 10 volt, very typical out there. Very often seeing that. That's kind of the go-to for dimming LEDs. It's kind of the universal standardized dimming protocol. In the States, I should say. Very state specific. But it's analog. What about digital? Yes, digital protocols, digital dimming, that sort of stuff exists. And that's some of those terms like DALI, for example. Who knows what DALI stands for? Digital Addressable Lighting Interface. That is a standard protocol that's out there. That DALI protocol, it's also kind of the go-to in Canada, in Europe, in many other parts of the world. DALI is just the industry standard. Everybody's familiar with it. And there are a lot of good, pros and cons to everything. Other digital protocols could include DMX 512. That really got its start in the theater. But DMX, Chris was talking about, are RGBW LEDs, color changing luminaires. Typically, DMX is the control protocol that is controlling color changing luminaires or moving heads. It's digital, meaning sending ones and zeros between the controller side and the fixture side. So digital controls offer some benefits above the analog stuff. So analog is beholden to the voltage that each driver is seeing. If you have a long run of fixtures, there is voltage drop from the start to the end. That end fixture might be a slightly different output than the first fixture. If we're doing color tuning via 0 to 10 volts, that last fixture might be a slightly different color than the first fixture because of voltage drop. With DALI, with digital signals, you don't have that issue because it's not dependent on the voltage. It's not measuring anything like that. That's very precise that you can do with these digital protocols. Questions on any of this stuff so far?
Yeah, can you do DC?
Yes, one can do DC. Ooh, go back. For power, you mean? Yep. Is an LED, DC or AC natively?
Natively, it should be DC, right?
Yes, indeed. Exactly. Yep. Yeah. Converts the power. So yeah, the LED device itself, again, it needs to see DC across it. That's another part of what the driver is doing there.
So if you have a DC source, you technically.
You have to meet the right kind of voltage and amperage characteristics. So as long as you have a controlled DC source, you might technically not need the driver. Yep. Yep. There's so many things, it's like technically yes. However, is it done? Might be a different answer. But yeah, DC, yep, since the LEDs are inherently DC, that's what the drivers are ultimately doing to the AC coming in. Tunable white, it's like Chris mentioned. Tunable white, how does that actually work? Well, there are often two different LED boards in that luminaire. You got your warm, 2000, 2700K. Then you have your cool and 2-channel driver. It's just balancing the output of both of those to blend it and give you some mix for any CCT within those two extremes right there. And there are a couple protocols, control side. How do we implement, color tuning with controls? A typical way is 2 0 to 10 volt channels, where the first channel to the LED, that'll control the overall intensity coming out of that fixture. The second channel will control the color. So here's our controller sending, let's just pretend there's 2 0 to 10 volt channels coming here. The driver then has a little microprocessor. It's interpreting those two signals coming in, and it is then blending its output to the individual boards. Okay, so dual 0 to 10 volt, that's one way to do this. We also have digital methods. Dolly is a pretty typical method for controlling tunable whites, and DMX can do it also. Exciting stuff. Dim to warm. Incandescence, the lower the current, the warmer the output. LEDs, absolutely not the case. So in an effort to kind of imitate that nice feeling, the dim to warm, that premium aesthetic that we all like, some drivers and some controls actually just do this with LEDs, so the LED itself is basically, it has those two different color chipboards in it, and the color output is just mapped at the driver level to the intensity output. Dim to warm, lovely. So let's talk about problems real fast, dimming problems. So when there are like incompatibilities between something, between the dimmer and the driver, for example, or if there's dirty power, if that zero cross on the sine wave, if that's a little hazy, if that's a little messed up, then we can have some problems on the dimming side. Flicker, the lights are really low. You can see them kind of jump around a little bit, little flicker. Slow start, where you start moving your dimmer up and then, pops on halfway through. Not ideal. Short stop, same thing. You're dimming down from the top and it just drops off partway down. These are some of those issues that you just need to be attuned to if you're designing, if you're specifying, just to make sure that everything, your drivers, your control systems are compatible to avoid as many of these issues as possible. Oftentimes the power on a site, the electricity splashing around the cabling, it might just be dirty power. There might be a lot of like motors, or it might be an old system. And so sometimes there's just nothing you can do on the lighting design side to address those issues. Just might be dirty power problems. Has to be addressed a different way then. Wonderful. Questions, comments? No apologies needed.
Base. And that will take 120, even if it's capable of both. Is that kind of like during the work that you're explaining, like it will work, but it might flicker or it might have some sort of issues? Or is that completely separate and we can just
Kind of related, actually. And to be so, you bring up a good point. Phase dimming really only works at, in practice, works at the with 120 volt incoming power. I'm not sure why it has more issues with 277, but it seems to. Chris, do you know, does this ring bells in your world?
Yeah.
Okay. Could you maybe like repeat the question?
So I have to start things, like let's say a fixture is compatible phase dimming. And it's, the fixture says 100 to 277. Set.
Okay.
However, I've been told from reps or people in the world that are like, it won't function on 277. We need to put that fixture on one.
If you're gonna put it on like a fade and these element.
Is that kind of the dirty power thing? Like it's just power, it doesn't like 277, and kind of like it. Sorry, I can keep.
No, it's okay. I digress just very shortly. Does anybody else find this interesting or?
Yes.
Okay. So like, let's say from Carl's diagram. This is time. And this is voltage. And let's say like, 120 here and 277 is here. And by the way, these are like root mean squared voltages, right? Like 120 volts actually goes higher than 120 volts instantaneously, right? And if we draw, right, how an MLV does, like Carl was showing, let's say our nice perfect AC sine wave is like that. And then we're going to come in and, cut this to like 50%. I drew that correctly. I'm pretty sure I did.
Looks perfect.
Okay, so this is MLV or right
Forward phase.
Carl's.
Leading edge.
Yeah, so we cut the beginning part of it. So there's two aspects of power, right? Power is equal to current times voltage, right? This thing has a power draw, and if my voltage is higher, right? What's like voltage is like an analogy to something else in like water. Sometimes water makes like a good analogy here. Pressure, yeah. So if you map current on top of this, if you have a higher, maybe we'll go back to blue here. If my voltage is now higher in my sine wave, because the frequency is the same, my voltage is now kind of spiking up here, and voltage is kind of like pressure. So imagine you have like a hose, and you're like the dimmer of the hose, and so you have this like valve that you're like switching back and forth on and off really fast. And imagine like I'm the person at the end of that hose, and you have like you have a fire hose, like legitimately, right? And I'm standing there like this, and you get to like shoot me with a fire hose, right? That pressure is really high, and I'm just standing there. And you turn that thing on,
Wi-Fi.
that water is going to hit me like really hard at 277 volts, not as hard at 120 volts. And since the fixture has a driver in it that is expecting some sort of voltage, there's a thing called current spike. This is kind of like getting like hardcore electronics here now. But the more voltage, aka the more pressure you try to shove through that electronic circuit, the higher that current spike is going to be. So current trails a little bit of voltage. So current, if you hit this up at 140 volts or 120 volts nominally RMS, you'll have your current spike do something like this, right? And then it's going to die down because it just lags a little bit because the voltage is the pressure that starts the thing moving, and then the current kind of ramps up. So if you have more pressure, you get more current spike, and there's a relationship there where you keep going higher and higher, pressure,
the current spike is gonna be super huge. And eventually this current spike is so high that it will literally start to fry the components inside of the driver that are receiving that power. And so, right, why would it be good to go to ELV? If we say ELV over here, and we're gonna ramp up like this. So imagine now, this is like, instead of the pressure being high when I open that water valve and I'm just standing there, imagine now there's somebody that is like at the pump and they're starting to turn the pump on. Well, it takes time for the pump to build pressure. So when I go ahead and I have 277 in this mode, there's no pressure here at the beginning when the electricity gets turned on, aka the water gets turned on. And so the pressure builds slowly and the electronics can handle it because the current spike is very low because the voltage, aka the pressure, is very low. So the current doesn't just like come out of nowhere and go bam, right? The current gets to build slowly and the current spike is very low, so it handles it much better. And then when you die off, when you cut the voltage here, the pressure just, drops. And so the current will naturally drop as well. And it's much smoother kind of current spike. So it's literally, to summarize that, it's literally, can the electronic components handle the current spike? And when you get an oscilloscope and you look at like how this stuff kind of works, that's what causes that. Now, as far as like dirty power, which was kind of like auxiliary to your question, this stuff causes dirty power because of the fact that you're switching the stuff on and off and you get these current spikes, right? And like, now you have to kind of think about, I have one pump. And this is like the one pump is like the power station, legitimately, right? That's like the power company. And now imagine you've got a whole bunch of hoses and all of us are like sitting there with hoses and we're just like turning them on and off like crazy. Well, there's one pump and the whole system is like trying to balance all those hoses being turned off and off, on and off at like high frequency. And they influence each other because it's one system. So if I turn all the hoses on, maybe you can imagine this, right? You got like one hose bib, but you got a whole bunch of sprinkler heads. Like, do all the sprinkler heads like work the same? If anybody's ever done their own sprinkler work, it's a giant pain in the ass trying to get them all to work the same. You're like, no, turn this one down, you're adjusting them. Right, so like, you could think of like each sprinkler head as a part of the electrical system. They don't all work perfectly, you have to kind of like balance them together. And the more pressure one gets, maybe the less pressure another gets. So that causes like kind of dirty power, and this stuff kind of influences that. And then the other aspect, if there's any electrical engineers here, is like phase offsets. So that's like power factors. Power factor also influences like kind of like dirty power because, as I said, like current, it trails voltage. You need pressure to create current. And so if the offsets get too crazy, if this stuff lags too much, that will cause problems in the whole system in general. And again, it's one system, not to go like too deep, but the more spikiness and the more lagging and all this kind of stuff, it influences everything in the system. It's kind of a weird thought to say like, well, my LED driver is literally like, it's literally influencing the water pump that's in the building next door. And that's why we try to balance all these things together. And when electrical engineers like balance different loads on different phases, they're looking at the power factors to balance all that stuff. In that way, there's actually a thing called current collapse, which is if you have the power factor too big in a building as a whole, it can influence the other buildings and eventually the whole system will like literally, fall, like the whole grid like shuts down. It's like not a good thing. So they spend a lot of effort to try to like not do that. Okay, that was a lot of technical stuff. Does that all kind of make sense? Okay. Sorry to digress.
Nice. No, it's good stuff. Yep. Appreciate it. Beautiful.
The term for all that is non-passively fail.
Non-passively fail. Non-catastrophic failure. Or its good friend, catastrophic failure.
Catastrophic failure.
Yep.
Does it blow up or does it just stop?
Yep.
Yeah.
Thanks, Chris. Beautiful. Sensors, also known as presence detection. Let's dive back in. Let's have some fun. Benefits of presence detection: energy savings, convenience of automatic controls, reduced maintenance. The less time your lights are on, the longer those lights last. So the specific technologies that these sensors use. Let's take a look. So PIR, one of our buzzwords from the initial slides, passive infrared detection. So the sensors here, sensors there. We have a little PIR sensor. It's looking for heat signatures moving around the space. Let's see, these ones are just daylight harvested right now. So I'm going to pass a couple of these around. And you can take a look and actually see these facets on the lens itself. But then if you look closer, you can see some actual like optics going on, reverse optics that are actually taking the radiation from the space and focusing them on the PIR sensor itself. So take a look and take a close look, and you can probably see what I'm talking about. So there's different zones on the PIR sensor itself. And when it sees that heat signature move from zone to zone, that's how it knows that somebody's there. That's how it sees motion. So a couple caveats. This is all line of sight. You know, it's not going to see you through the wall, obviously. It needs to see that directly. You get some funny behavior around windows. Sometimes windows are bouncing that electromagnetic radiation off. But oftentimes the sensors are just seeing through those windows, right? So they might accidentally pick you up on the other side, cause some nuisance behavior. Ultrasonic detection. This is now one of the secondary technologies in addition to PIR that is in a lot of sensors. And ultrasonic, it's emitting ultrasonic sound waves. So this is kind of like almost literally like sonar, sending waves out into the space, listening for the bounce back. And if that bounce back signature changes, that's how it detects occupancy. So this does not need line of sight. This can look around cube walls. This can bend around corners, stuff like that. So it gets you away from the line of sight detection. Some downsides are that this is pretty prone to nuisance tripping, right? Air comes on, ceiling might rattle. All of these things can re-trip this ultrasonic type technology. A third type of technology that we don't have a slide for, but it's microphonics, right? So PIR is pretty much always going to be in your motion sensors, but then your secondary could be ultrasonic or could be microphonics. Just a little microphone listening for sounds, listening for people's sounds out there. And then in that way, it can re-trigger the lights, keep the lights on, see around corners, that sort of thing. So several different technologies that we use in these sensors to detect if you're there or not. So false triggers and problems, we just kind of talked about that a little bit. It goes both ways, you know, so the sensors, they do their best, but they're not perfect, right? So they might turn the lights on when nobody's there. You know, they might see a car go by and they think, oh, they're moving heat body, let's turn the lights on. There are ways to kind of tune the sensitivities of these technologies, you know, so you can dial the PIR sensitivity down, dial the ultrasonic down, dial the microphonics down through the software, for example. Then same thing, sometimes it's turning the lights off when people are there. You know, you're in the space, but you're just typing at your computer. You haven't moved enough. So it's like, meh, nobody's here. Turn the lights off. Very annoying. The way to combat that is just thoughtful, diligent design. You know, be intentional with where you put your sensors. Be intentional with the lenses, the detection radiuses that get selected. Oftentimes that question itself is a bit of a trade-off between the engineer, the specifier, and the rep or vendor, you know, because every system, you know, company A's sensor might have a 16-foot detection radius for minor motion. Company B, that might be a 10-foot detection radius for minor motion. You know, so deciding what that sensor layout looks like exactly, you know, deciding the other options that you want on that sensor. It's a bit of a balance between the specifier and the vendors for the most part. All making sense so far? Wonderful. That's what we already talked about, dual tech. So these are kind of some the industry terms for these sensor types. You can have PIR only, or you can have dual tech, so those are some vocab words for you to throw out there. Impress your friends at parties, that sort of thing. All right. So the sensor, again, technically it's really just a little device, and it can be packaged in all these different form factors, all these different packaging. So it's a bunch of what we have up here. What just got passed around, that's just your typical ceiling sensor, right? Goes up on the ceiling, easy peasy. But we have a lot of other options. Wall mounts, corner mount sort of thing. This is a massive literal ambient light collector. So this sort of thing, it's self-powered, it's wireless, but it doesn't have a battery in it. So stick that on your wall, in a corridor, stick it by a front door, something like that. Catch people that way. Here we go. Industrial. So imagine a warehouse with a bunch of high bays. You can hang one of these off the end of each high bay. Now it controls itself. What do we have here? Same sort of mounting thing, but this one goes outdoors, So your site lighting, parking lot poles, pedestrian poles. This could be type of sensor that you put on that pole. The sensor itself, it's probably both a photocell and a motion sensor. So, you get these hybrid sensors, hybrid technologies out there, different ways to mount them. And, in that way, you have a lot of different options to meet energy code and do what you have to do there on site. This little thing, we haven't gotten to this yet, but cute little guy right here. Stick this on a mullion, basically. It's a magnet. This one does not have a magnet. Open loop photocell. We'll get to that slide in a little bit, but you can point this out the window on a mullion, and now it's just looking at what's going on outside. You're able to use that to maybe turn your exterior lighting on, turn your wall packs on when the sun goes down. Mullion mounts, open loop. Switch mounted sensors too, of course. It's a classic wall box sensor switch, excuse me. Control multiple loads here, a light load, a fan load on this one. Good stuff. So, bunch of different ways to mount your sensors. The power for those sensors can come from different areas too. You might have heard like line voltage controls. A line voltage sensor itself, and just connect it straight to your 120 or 277. Then that device has the actual line voltage relay, turning the lights on and off and on. So when you hear that term line voltage controls, typically that's referring to the line voltage relay within that device itself. Low voltage controls, on the other hand, similar looking sensor with a little power pack. So this power pack now, it's doing two things. This has the relay in it. Lights on, lights off, but it also has low volt aux leads to this sensor. So it's connected to the sensor, providing power. The sensor is sending a signal back to the power pack, sees people, turn lights on. No people, lights off. So low voltage control. So this would be a low voltage analog, technically, is what this little setup right here is. Sending an analog electrical bullet back to the power pack. Good questions on line versus low voltage controls. That comes up out there in conversation a lot. Good to kind of have an understanding of what's going on there. Beautiful. All right. Sensor coverage. The sensor you put in a private office would have a different coverage pattern than what you put in a corridor, for example. Private office, you want to cover that minor motion. Typing, moving your mouse around, leaning back in your chair. That's very different than somebody walking down the corridor. So there are different sensor options, different lenses that pick up, different sizes, different scales of movement, essentially. So maybe you as the specifier are selecting your minor motion versus your large motion, or which sensor goes where. maybe you aren't and you're leaving that to the vendor. That's fine. But somebody out there is making that decision. Exactly the same. Yep. It's the same exact product, just a different, the plastic lens, different lens on the front. Yep. Some of them are even field interchangeable. Turn your minor motion to a major motion. Great. Off you go. Occupancy and vacancy mode. We're back. We already talked about this. Just give that a quick gander there. Make sure that still all makes sense to you. Lock that one in. That's another kind of common term out there when we're talking vacancy mode versus occupancy mode. And again, driven by energy code for the most part on what you need where. All right. So all these devices, you know, it's 2025, so everything's pretty much programmable at this point. So some of the things like on a sensor that we can change, it's the timeout. Do you want it to turn off after 10 minutes or 20 minutes from when somebody leaves? Well, you can set that right in the sensor. What do you want it to do after that initial timeout? Do you want it to maybe dim the lights down first for after, 7.5 minutes and then off after 2.5 more? What is the sensitivity of that sensor? Do we want to pick up, the Jeep Cherokee driving by outside? No, you don't. So crank the sensitivity down or up, depending on the spaces, depending on what the nuisance behaviors are. You can fine tune what's going on with that sensor. Great. And that was motion. That was presence detectors. That was motion sensors there. Jump gears a little bit over here to daylight sensors, light detection. Daylight harvesting for the most part. All right, so daylight harvesting, when there's 100 foot candles of daylight coming in, you can dim the lights down and kind of, to maintain a target foot candle level. So in a classroom, for example, you might want 30 to 50 foot candles on the work plane. If all of that's coming in from the windows, well, heck, save some energy, dim those lights down to 10%. That's what daylight harvesting is. It's done automatically. These fixtures up here, they're kind of dim. They're a lot dimmer than they need to be. Literally, right now they are being daylight harvested from these things. We have our Broncos shining right into the daylight sensors, and right here in front of us, daylight harvesting is happening. Light harvesting, if you will. We'll get there maybe. So good stuff, fun stuff. All right, let's talk about closed loop versus open loop. This refers both to kind of the arrangement of the sensor and also the sensor itself. So closed loop, that's when we have a sensor on the ceiling pointing straight down, reading the total light levels in the space. So that's going to be your daylight, your natural light, plus your electric light levels. And closed loop is then used to meet a target foot candle level. 40 foot candles, it's constantly reading, feeding back to the system, adjusting, and settling as close as it can on that 40 foot candle level. It's important to place the sensors in an appropriate location because it's looking straight down, and what's below it, might be this black carpet, it might be a white desk, it might be the top of your head. So in this case, that's where the actual placeholder. Looking straight down, that's kind of dark. What's interesting is that the final node, final carpeting, final FFE in the space can drastically change what the sensor is doing and what it's doing to the lights, which is kind of interesting. So as part of the programming process, there's this calibration step that happens with daylight sensors where it kind of tracks, okay, this is typical light during the day, this is typical light during the night. It kind of gets a feel for what the space looks like throughout the course of the day. And then it accounts for that, automatically calibrates the output accordingly, if that all makes sense. So closed loop daylight sensors, which implies open loop daylight sensors. That was that other little guy that we passed around. Open loop is just staring at the sky, purely looking at natural lighting. So that can be used for sight control. You know, when it gets dark outside, turn the lights on. When dawn hits, turn the lights off. That's open loop photocell design. Good? Excellent. So switching gears a little bit, that was daylight harvesting. How do we save energy? Now there's an inverse to that, daylight compensation. And this is interesting. It's not something I personally hear much about, but it exists. And this is for situations where could be retail, something like that, where the visual contrast, I'm sitting here, I'm looking out this window. There's a ton of daylight coming in that window. The room looks very, very dark in comparison, you know, and if you're like dimming those lights down, just even more so, you know, so it might have a weird sort of like emotional feel, weird like security ramifications there. Could be strange for retail, you know, if you're trying to sell product, but the light is washing out your product. Well, okay, let's bring the interior lights up a little bit to lower that contrast. And so your eye has a better chance of actually seeing what's going on the inside. Daylight compensation is what that's called. Has anyone ever like had to do this on a project or heard about this? Because I have not ever. Something to keep an eye out there for. And maybe that's you. Maybe you bring it to a project, retail or something like that. Have fun with the permit reviewer on that one. Yeah. Yeah. Oh, yeah. Yep. The light was so bright it was burning the product. Yep. Oh my gosh. Holy. Yep. It was LEDs that were doing that too. Wow. It's a lot of light. Oh my gosh. Yep. That's a whole lot of light. Interesting. But yeah, that would be the exact sort of application for this. You're selling makeup product, you're selling something where the colors matter. You know, don't let the daylighting wash that out. Cool. Okay. We talked about what you can program with aux sensors. Same thing. What can we program on the daylight sensors? So a couple different things, of course. What is that foot candle threshold? 10-foot candles if you're in like a lobby or a circulation space. 30 to 50 if you're in the classroom. It's adjustable. The dim range. Do you want it to turn lights completely off when there's enough daylighting in there? Or do you want to keep them on maybe to like a floor of 10%? You know, similar thing on the top end. You can adjust like the top end trim for these things. Fade rates. If I shine a flashlight in one of those, do we want to see that light immediately dim down? Or do we want to spread that out a little bit so that it's not distracting to people in the space, you know? So you can adjust that fade rate, 10 seconds, 10 minutes, whatever you got to do. Calibration, we're talking about that a little bit. So lots of different options that you can actually program with these sensors. All righty. Let's keep powering through here. Network systems, we're getting close to the end. So let me pause for a second because this network systems, you've all been doing great. This is a very important one to pay attention to just to really understand this concept again. I know we've hit it a little bit, but repetition review, it's the best way to actually learn something. So let's dive in. Networks are everywhere. Oh my gosh. So like we said, a network is a system of interconnected components that are talking back and forth, you know? So this could be multiple power packs, you know, multiple zones within the same room, all talking to the same sensor. That's a little mini network. Could be this room talking to the lobby, talking to the time clock back in the electrical closet, slightly larger network, right? Different layers, so different outputs and different inputs to these systems, right? So output, lights are on, lights are off. Lights are 50%, lights are Broncos. That's an output. Inputs would be like, oh, we see motion, so the sensors are an input device. They're, waiting for something to come from the environment, a button press, somebody to move by, the daylight to come in, and then that affects the outputs. Walk in, lights turn on. Press button, lights turn off. Inputs, outputs. So network systems, why do we do it? All sorts of reasons, of course. A lot of it's coming from energy code again. So a time clock and a network, there's a lot of overlap between those two things. They're not direct synonyms, but with system we're looking at up here, for example, we have our network head end. This is also the time clock. This is a computer and it's doing a lot of different functions, of which time clock is one of those. So in that way, energy code is really kind of pushing the concept of networking controls. The IECC C406 additional energy efficiency measures. Some of those requirements are networked lighting controls because of the savings that this unlocks. When we have an entire building connected to a brain like this, I can get into the software and I could set a global high-end trim of 80%, for example. So no light in the entire building will ever go above its 80% output until you change that. So that's a feature that you get with the networking head end with a network system. One of the ways to get that. So cool. While we're on the energy code slide, and I'll bounce around a little bit, but we all had a lovely time on Thursday talking a little bit about this. You have all practiced, or many of you have practiced this in your day-to-day lives, but it's still it's a polarizing topic. Does anyone have any conversation points, questions about energy code, anything to chat about here real fast?
Yeah, you have the two items. I think there's also a 600 square foot. There's zones and things like that. Does that so harvesting?
Yep. So those are two different, that's a good question. Yep. Current code requires a primary daylighting zone, which is the head height of a window. We've got like a 25-foot window back there, so that's pretty crazy. Lots of daylighting in this space. So your primary zone, then your secondary zone. That's only kind of like one layer of it. Superimpose your 600 square foot limit on top of that. That's another code requirement. Open offices, the control zone can be no greater than 600 square feet. So that layered on top of your daylight zones can result in a lot of zones, zones within zones, if you will.
Yeah.
Yep. But yes, those layers, that's the right way to think about it. And that's what code is saying for sure. Yep. Yeah, so each 600 square foot zone might have 3 subzones within that, right? Primary, secondary, and general lighting. So it can be a lot of stuff. It's a lot to keep in mind. Multiple ways to skin that cat when the time is right. Okay, let's kind of zoom through the different scales of the system. So what's going on at the room level, right? That's just these basic parts and pieces that we're looking at. So energy code says we need a sensor, says we need a dimming, manual control and dimming. So here you go, sensor on the ceiling, dimmer on the wall. And then you need something to actually control the lights, load control here. So kind of just a few basic parts and pieces, or maybe it's just a single line voltage sensor, turning the lights on and off based on occupancy. Just a couple basic devices is usually all that's going on at the room level. And these basic devices are capable of all sorts of different things, depending on the exact product, depending on what's going on here. So, you could be programming these devices with an app on your phone. You could be hauling in a laptop, programming it that way. Could be like a little handheld remote, writing the settings and just blasting them to each of the devices, all at the room level. Scale up, put all those rooms together. Now it's a single floor, a single tenant of control. Bunch of those little devices repeated over and over again. There might be a gateway involved at this point, a brain. There might be some integration to other systems like fire alarm, for example, where we take a signal from the fire alarm system and that turns all the emergency lights on, for example. Could be schedules, could be time clocks going on here. All sorts of things could start to happen at this level. Keep scaling up. Now you're controlling an entire high rise, for example. At this level, there's probably a building department, a facilities management department. They need to get involved. They might tell you what to do with that lighting control system. They might have preferences, they might want to integrate lighting controls with their building automation system. They will tell you, and the things that you then, as the specifier, have to keep in mind, just start to keep growing a little bit, more things to pay attention to, more things that you have to specify your system to be capable of. And then just keep scaling that concept up, Now there's a whole campus or whole portfolio of buildings that need to be managed. It's even more important at that point that you as a designer, you as a rep, you as a vendor are coordinating with that facility department to make sure that you're doing what they need so that they can keep manage their buildings, manage their facilities in their own way, the best way possible for them. So what you'll see is as the scale zooms out, there's more and more features, more and more coordination, more and more going on that needs to be kind of discovered up front, articulated into your sequence of ops, into your intent, and into your design. All right. Network architecture. A couple different ways that all this stuff talks together, right? It could be wired, wireless. Over here, got Cat5. So this is a digital wired system going on over here. Ones and zeros going down to Cat5, right? That power pack example, the standard low voltage power pack and sensor. Analog low voltage. This is just pulsing little 24 VDC pulses along the red wire to the power pack. Analog low voltage. Wireless. Again, this is a solar collector. It's sending wireless packets to the load controllers, to the power packs. And the switches themselves, batteries on the back, wireless, sending wireless packets to the power pack. And these are all just the different options that are available. There's a time and a place for each, pros and cons to each, reasons to combine. Oftentimes a final design will be a combination of many of these things. What you need to do in a storage room is not the same thing that you need to do in a conference room, for example. Questions on this? Excellent. All right, let's talk about wired versus wireless real fast. Wireless, kind of won't say a buzz term. It's even been around for a long time too. But a lot of questions still out there about, pros and cons of wired versus wireless controls. So on the wired side, it's very reliable, secure, it's harder to hack something that's physically here than signals just bouncing around in space. Less equipment cost, not necessarily true all the time. On the con side, if you're installing a wired system, it's a little more costly because now you're running communication cable all over the place. Where on a wireless system, there would be no communication cable, and therefore none of the labor, none of the commodities required there too. Bless you. Wireless, pros and cons. Wireless is more flexible, if you have these self-powered or battery-powered sensors, just You can literally stick them on the grid, stick them on the ceiling, off you go. Very easy, you know, wireless powered, these little remotes, stick them on the glass wall if you need to, no back box required, easy, low labor, low effort to install. They're getting a lot more popular because of that ease. It makes them more cost effective. Almost just immediately, wireless controls versus a comparable wired system is going to be less expensive. Oftentimes, the material is less, the labor is always less. So flexible, less expensive, not quite as secure, just because you have those signals bouncing around. There might be that Bluetooth beacon that is locatable from a bad actor, you know? So just some of the pros and cons here between the two systems. Digital versus analog. We talked about this a little bit already. You know, analog, example is 0 to 10 volt, right? Digital, an example was Dolly. Ones and zeros over there versus actual like electrical signals, electrical outputs over on the analog side. Questions on either of these? Wired, wireless, analog, digital. All makes pretty good sense. Cool. Y'all are doing great. Last section, general considerations here. This will be kind of our lighting controls wrap up and review here. So, term you've possibly heard before is commissioning. And commissioning is often used loosely. Very technically, it means kind of third-party commissioning, third-party functional testing. It's the technical term for commissioning. It's used more broadly, however, and a little more in everyday use as also just system programming, you know? So from that regard, you know, commissioning or programming on these kind of fancier digital systems, this is now a step that's required pretty much on every project, you know? We've installed the parts and pieces, you know, we've specified everything just so. Now we have to come in and program them to the project-specific sequence of ops. You know, set those timeouts to 10 minutes, set the fade rates to be appropriate, set the foot candle, the daylighting targets where they need to be, make sure everything's in vacancy mode that needs to be, et cetera, et cetera. So that commissioning, that programming process is pretty much always something that occurs, and that's by, you know, the vendor or the rep or the system integrator actually going out and doing that programming. Now, there is the other side of actual third-party commissioning, you know, where that's a different entity. That's a legal thing directly with the owner where they come out after the system is programmed and they just check. They're like, okay, you know, bathroom lights are turning off after 20 minutes, check. Office turning off after 10 minutes, check. That commissioning is done to ensure for the owner that the system is performing the way it was designed. You know, so that's a really valuable service for the owner because, you know, it's not just lighting controls that are being commissioned, it's mechanical, security, it's AV, it's all of that stuff. Coming in and actually verifying that, yes, these systems are doing what they're supposed to. Excellent. Skip that one. Documentation. We talked about the intent narrative, also known as the sequence of operations, more or less, tells you what the system actually needs to do. In addition, you can publish these diagrams, publish risers, typical wiring diagrams, and that's an additional piece of information to actually show the parts and pieces now, how they connect, how they're talking to each other. Can be very helpful on larger and more complicated projects here. And obviously a couple different ways to do it, a couple different layers of detail to provide. All right, resiliency. So some things to keep in mind. As a system grows, as it has to do more and more, as it gets more complex, kind of some of the more and more risks are introduced with that system. Risks of integration failures, for example. There's just more and more to track and more to keep in mind as that system gets more capable naturally. Issues with controls. One of my favorite slides. So, yep, if you've spent time in this industry period, if you spend time with end users, with engineers, with anybody, you hear a lot of like similar complaints, a lot of similar feedback, like, oh, it's too complicated. We just want simple controls. Or the lights in this office don't work. They never turn on when somebody goes in there. Like, well, end user, that's because it's vacancy mode versus occupancy mode, and they don't care, obviously. So, a lot of the issues that we see with controls, it can be an informational thing. There's simply people don't understand IECC 2024, for example, because why would they? They're just a nurse, trying to operate at her nurse station. Installers might not know what the heck they're doing. Engineers might not know what they're doing. Reps might not know what they're doing, what they're talking about. So half the battle is more of an informational battle than anything actually going on with the system. The sequence of ops might be uncoordinated with what the plans are showing, or it might show in an unconstructible sequence or something like that. There could be a mismatch of expectations, ownership, they just want a simple app on their phone because that's what they have at home with Philips Hue. So why can't this just be an app on the phone? Well, another, it's an informational thing. The other half, of course, could actually be issues with the parts. Maybe the rep provided a large motion sensor when they should have provided a small. So now that office is always turning off, even though the person's in there waving their hands. They're just, not in the right detection pattern right there, so that could be an issue. Could be improperly wired. The contractor could have connected there, and this happens all the time back in the day. This gray wire on the 0 to 10 volts looks an awful lot like a 277 volt neutral. And so you tie that to 277 volt neutral, poof, lets out the magic smoke. So that could be a problem. Cat 5 could be made up incorrectly. There's all sorts of different issues that could show up. And we all just do our best to do what we can at the given moment. Hopefully we all know a little bit more than we did 2 hours ago. Are there any final words up here, vocab words that anyone's curious about, or are we all at 100% understanding now at this point?
Just curious.
What about it? I've heard that Vail has adopted it. Anyone else heard of any others that are on 24? Maybe. They just got onto 21, actually. Since Boulder, they're their own energy code, City of Boulder Energy Conservation Code. It was based on 2018 up until like the last year, honestly. Yeah, which is a little backwards, but there it is. Yep.
What?
I'm not sure.
Okay.
Yep. Which is a great question. If any. I heard the same thing from one of your people. Yep. Yeah, so if anybody knows about plug load, you probably know that it's a bit of a pain in the butt. So certain jurisdictions, certain states have just waived it. They're like, nah, we're good. And yeah, rumor is state of Colorado is considering that. So all plug load control might go away. One thing that's important to note, actually, right now in real life, City and County of Denver, they waive plug load control for renovations. So only in new construction in the City and County of Denver do you have to provide plug load control. Not sure if that means anything to all of you, but it's really important to keep in mind. True story.
Is that just like controlled receptacles or what other types of plug loads?
Yep, it is control. Exactly. So when we say plug load control, referring to, yeah, a section of code C405.11. And it says, oh, in all of these different space types, offices, private offices, conference rooms, break rooms, classrooms, you have to control 50% of the convenience outlets, you know? So that could be half switched, you know, where only this one is switched and this one is not. That's 50% of the plug loads, you know? So run that around to all of your plugs in a space. Now you are compliant with C45111. Plug load control, automatically controlled receptacles, all the same terms pretty much. Anything else? Excellent. Excellent comprehension. In conclusion, controls are the future, controls are the best.
Except for the plug.
Except for that, yeah. And maybe some daylighting. And when it gets too complicated. But apart from all that, controls are the way. Appreciate y'all. Just shout with any questions and let's take a little break here too. Great work hanging in there. That's a fun one, yep. So yeah, there's beverages in the fridge if you're interested. NA beverages, sparkling waters, that sort of stuff. Yep. I know. Sorry to disappoint. The red, yeah, the red versus other. Just gotta ask. Yep. Yeah, and it works about 60% of the time every time. So yeah.
Time.
Is it? Oh, that's not so bad. Yeah. If I really wanted to, I could probably go screw around with it and make it faster, but yeah, that is not too bad actually. So yeah, seriously, go if you want. Pardon? Let's like 10 minutes-ish. Yeah. Yep. Oh yeah, totally. Yep. Do what you got to do. Be back in roughly 10 or just keep hanging out. It's all good. For something. Oh, this. Take, I guess.
Yeah.
This is like super semi-military. So we're doing the rights.
That goes back.
Yeah. Let me explain about it. Because like it can be, it can do more than not much more. It's a.
Yeah. Oh, I think it's maybe in Minnesota. Like, you know, it's like, I actually designed it.
This is you? Yeah, the expert right here, the Rubik. It's basically a little like,
I know more about this fixture than anybody else.
well,
You have like a pattern in mind?
I
The idea is to give a pattern. Like, does it sell a lot, like, I don't know, Williams? No, they can buy, they can sell it, you can, yeah.
so
Yeah, it's still available, I don't think they do a ton of sales out of it, like,
yeah, Mark Rubik.
yeah,
So yeah, it's pretty much like these this grayscale.
You're on.
That is like the switch.
That's usually where it gets utilized, and I'll probably installed it,
Rubik touch sheet.
I
With
don't
like
quote me on this, but
dedicated.
like in Antarctica.
Yeah.
To like.
Yeah, the full grid, just like a 3x1. There's some corners around.
Blue and it feels like, oh, we've got it.
Yep. And that's part of it, is like the power output, the actual light out. Even, yeah, even as it's like so one goes down, the other goes up. Yeah. There's anything involved in this.
Yeah, dude,
Is it?
this is where I like got the chops on color. Like,
Yeah.
it, like programming of like how it works, yeah. Yeah,
Chris, is this a beauty fixture?
Mhm.
Okay.
yeah, I think it's Mark, architectural, if I'm correct. Yeah, it's good for this. Yeah.
You want to get plugged in here?
Yeah, sure.
Yeah.
Oh, yeah.
I don't know, we're gonna try to move fast. If you do that. I mean, I would ask the class if they wanna do lunch here or like kind of push through it and bail. I mean, we'll probably go till noon. At a minimum, I think. Like it's kind of clean right now. You guys want free lunch? I would eat free lunch.
The Pepsi.
Yeah, I'm going.
Okay.
Maybe we check in after the next module.
Yeah, let me start.
Yeah. And if anybody wants to stay for lunch, then we can make that happen.
Yeah.
Yeah. All right. I'm gonna disconnect the app. Ooh.
That's the HDMI I need.
That's the one.
And then I think. Hey, hey, Ali, can you maybe it's on the co-host so I can share screen? Yeah. Grazie. Okay, is everybody awake? Anybody need to do burpees? Let's go screens. Like if I yeah, I can share now. I just want to get the right, there we go, screen 2. Zoom didn't want to recognize. Okay, does that look good?
Good.
Okay, solid.
Cool, thank you.
And I want to make sure, can you hear me on it or is it?
Say something?
Hello, check 1, check 1. All right, cool. Okay, are we back?
And then if you start your camera, I'll show this like room. Or should
Owl might not be plugged in.
No.
I did plug it in.
Not sure.
Yes, looks great.
I'd like to move this like somewhere else. Or hide video panel? No. Why is this hide flavor controls? Bingo. Okay.
Oh, you are plugged in.
I am plugged in. I took the cable and I plugged it in.
Amazing.
Okay, should be good now, thank you.
Okay, optical efficiency. So we put in like 20 watts into a troffer, right? It's got what we call luminous flux. Do you ever remember what that metric means? Luminous flux. Negative? Lumens, yeah, lumens. Lumens are a unit of luminous flux. That's the unit we use, but what is the key word there is flux. What does flux mean? Like if something is in flux. Sure, yeah. Yeah. A rate of something sometimes, right? So luminous flux is the rate of photons going through, coming out of a thing, going through a thing, whatever. And it is the rate, it literally is the rate of it. So like we turn off the lights, what happens? It's not meant to be like a stupid question, although it kind of comes across that way, right? Like we turn off the lights, what happens? Oh, the lights go off, yeah. What happens right before you can't see anything? Yeah, it gets dark, right?
Over a period of time.
Yeah, over a period of time. How quickly is that time?
Pretty fast.
Pretty darn fast. Yeah, because light travels at how fast? Oh, module 1. That was kind of loud. Louder than I expected it to be. Yes, exactly, right? So I mean, the light's coming out of this thing, we kill the power, right? The luminous flux, the rate of stuff starts to die off because we killed the LED output. And for a very, very brief moment, right, those photons are bouncing in between, and they're coming into our eyes, right? And they go down. So the luminous flux is always changing, but the luminous flux is the rate of photons that are like coming out of the thing, right? Also known as lumens. And if our optical efficiency is lower, right, what does that mean to our well, 80% my blue different is a unit of luminous flux. That are fully transparent tend to be pretty high optical efficiency. And as you kind of do more and more diffusion, this is kind of, right? This both absorbs some stuff, lets some pass and reject. And the more bounces something makes, what happens? The less bright it is. Yeah. Why?
Oh,
It's being absorbed. It's losing because it's being absorbed. Right. So which one is more photon? That one. Why? That's a lot more stuff. Absorbs a lot more stuff. So all these things, the colors of stuff, the materials, those that absorb, what's made out of affects optical efficiency of a luminaire. Type they are, or kind of what category of product they are. The listings, is it red list? Is it, well certified? Well certified? We can just the criteria that you would classify light as, right? You can also say the performance of it. How much energy does it take in electrically? What's the distribution? And downlights are that way because they put all the light down. We could say, well, 100% of the light is indirect. This is a fully indirect fixture, meaning that it all goes up towards the ceiling. We can mix those two things together. So this one here, you can probably imagine fixtures where like you can't, we don't have a great linear in here, but a lot of linears, right? They have like a lens on top, the whole way goes up or down to go to the side, really. Or you can make the whole thing glow, right? You know, like a square shaped kind of luminaire, right? That's an extruded linear, all whole thing, right? That could be something kind of like this, right? And you can adjust it. You can say, well, I want 50% of my light up, or an 80% down, or 50-50. I want to do a battening up and what's called Lambert down. That term before Lambertian. Did we go over Lambertian? Did you go through in this class? Okay, so Lambertian. You can look at Google, that's right. But Lambertian just means it's nice and diffuse and soft. Lambertian look like this or like that. Lambertian distributions tend to be pretty nice, and most things that are very matte have a Lambertian reflection or diffuse reflection, perfectly diffused reflection, and Lambertian are synonymous. This thing keeps like popping up here. Okay, we're spending a lot more go. 10 minutes. We'll order something special for you for lunch. What do you want? So type 1, you know, type 2, type 3, type 4, type 5. The type 5 is kind of unique, and the type VS, what do you think type VS stands for? Type 5 square. Names are so creative. You know, right? This isn't even a square. Very hard to get square, you know, kind of pattern on the floor. But these shapes are intended to be the light that goes onto the ground. So where would I use like a type 5? Parking lot, bingo, quintessential example. Or would I use a type 1? Sidewalk. Could be a sidewalk. Any other ideas? Sidewalk's a good one. Corridor? Could be a corridor. Usually these would be like exterior area lights. It's usually what we classify these as. But fundamentally, it's kind of the same distribution. A lot of times we generally use type 1s in like very rural roads. Think of like a 2-lane road where the fixture is gonna like have like an arm mount that's kind of like over the road. You can get like a lot of coverage of those 2 lanes. Now, if I didn't have an arm that stuck out above the 2-lane road, but instead the fixture was like offset from the road, right? It has like 10, you know, it's like 10 feet back from the road, something like that. I might want to take that light and just kind of push it forward away from the fixture a little bit, so I light the road over there, right? Type 3 does that even more, pushes it even more forward. A real common pattern in parking lots used to be to use 2 type 3 heads back to back. So I can barely get my hands like that, right? But I just have 2 type 3s that are pushing light like this. The funny thing is when you do that, it looks almost exactly like that. Not perfectly, but you know, close to it. And then type 5 is real common in like pedestrian kind of walkway areas where I just want some nice, you know, light in this area. Like just give me some light on the ground. Any questions on those ones? Again, these are IES type distributions. And they're usually for area lights. Bug ratings. Has anybody had to work in jurisdictions that use bug ratings or MLO, model lighting and ordinance? Boulder's got it. I think they actually, I think Clanton Associates actually helped write it, if I'm not mistaken. Okay, so bug. The B stands for backlight, the U stands for uplight, and the G stands for glare, not forward lighting. Very confusing, but I think they called it like buff. It would be very confusing, right? So you get glare. So like if I'm driving down the road in my car, right, where are things that are glary? Like where are light sources that would be glary?
Lights.
Yeah, headlights coming right at me, right? What else? What if you're heading eastbound I-70, 6:50 in the morning? Sun, right, just coming up over that thing, and you know, it's amazing that we don't have more accidents on that, right?
What's it for part of the season for that exact reason?
I-70, I don't know, I've never, especially in Denver, I don't think they close it. Yeah, but I used to drive downtown to VI for work like almost every day, and that sucked in the winter. Right, so think about it this way, right? Things are in kind of like not outside or near my periphery, but they're kind of in my central vision, creating the most glare. Well, if you've got a fixture in the highway and it puts a lot of light kind of straight out, it's basically acting exactly as the sun would on the horizon, right? The light fixture is kind of out there a little bit, but same angle. So what they want to do is limit the amount of light that's up in this area, right? Same thing here. I used to live over near like Sloan's Lake area, and there was one of those old high pressure sodium lights that was like on the street, you know, and like there's an alley behind the house, and basically like on my window just had this like yellow cast of light like shooting into the house at night. It was so beautiful. I loved it. Yeah, you know, like you just the curtain shut the whole time. They can't even use that window. Although not that the alley was very nice, so it doesn't really matter. Okay. And then uplight. So uplight causes what? Light pollution. Yeah, light pollution. Bingo. Nice teamwork over there. And so the bug rating has kind of like 3 components of it, right? How much backlight does it have? And for a type 1, you may want some backlight. right? Because the source is kind of directly above what you're lighting. Now, as you start to move towards a type 4, you don't want a lot of backlight, right? This is just a way to classify it. It's not like there's a right or wrong. This is about the practitioner knowing what their tool is, right? So if you want no backlight, the bug rating tells you that this fixture has no backlight or it has some backlight, right? Kind of depends on the application. A lot of the codes nowadays in the model lighting ordinance say that for a parking lot, right, you have like fixtures around the outside of the parking stalls, like they're in the grass at the edges. They want to put all the light in the parking lot. They don't want to put any light back against like the edge of the property, right? Because that would be considered light trespass. And the light is kind of going back on somebody's property. The worst offenders of this are what kind of parking lot? A lot of cars in them.
Car dealers.
Car dealers, yeah. They're new, they're shiny, they weigh 10,000 pounds, they're called Hummer EV. I love that car so much and I would never ever buy one. It's just like the obsceneness of it. It's like, I got like 1,200 horsepower in this like giant 10,000 pound truck. May or may not light on fire when I crash.
Chris, I have a question.
Oh, you have a Hummer EV?
No.
Oh.
Sorry.
Can I drive it?
I could have meant something else.
Oh no, I think it's an amazing car.
But I know the BUG ratings are like 1, 2, 3, or 0. Like, what the hell is the 1, 2, and 3?
Yeah, that's correct. So real simple. Numbers go down, less.
Yeah, what is it measuring?
Yeah, so it's measuring the amount, like the B0 would be 0 backlight.
Okay, what's B1?
I'd have to look up the actual chart. There's a chart.
It's like 1. output.
Yeah, it's just one lumen. No, I think it's in percentages, if I'm not mistaken. So don't quote me on the numbers here, right? This is like completely off memory, but like B1 might be like up to 10% of total fixture lumens can go backwards,
Okay.
something like that. And then as you go to 5, it can, it says like up to 50% or something of that nature.
Okay.
They're not, it's not a linear correlation based on my memory, but I don't remember the specifics. So what I do remember some of the glare stuff. It's like, as an example, it says for G0, like no glare, it'll say 0% in the FVH zone. And then only like 2% of light can be in the FH zone. So it's setting percentage dictations of how much light can be in each zone. And if you look at the way that this is segmented, right, we've got 1, 2, 3, 4 zones. Plus 4 zones, plus 1 zone. So we have 9 total zones because uplight has 2 zones. So 10 total zones, right? And you get percentages for each of those zones per the ratings. And the model lighting ordinance kind of says like, okay, so for this use case, you are allowed a B2 U0 G1. And that's kind of how like the mandate goes. So you must comply with fixtures that are at that level or better, is kind of how that works. Everybody envision that? Okay. Good question. And yeah, you can, is lumens? Yeah, number of lumens, right? Okay. Thank you for the correction. There's a chart, reference the chart, not what I say.
How causes the exterior LEDs to be?
Oh, it's a serious question.
Because I don't name names. Yeah, because
What Acuity? Acuity had a big problem with this.
don't say cutie. That's good.
Everybody had a big problem with this. It wasn't on Acuity. Yeah,
Everyone.
yeah. Well, it's an issue of statistics, right, Carl? So like Acuity is like they're the biggest lighting manufacturer in North America, and they have the most sales out of any lighting manufacturer. Well, when you have a problem with your LEDs, right, who is it going to affect the most?
Big numbers. So.
It's still a huge number. Yeah, you take 10% of the largest number, 100 billion fixtures out there.
Yeah.
That's probably not true, but a billion fixtures maybe, a couple of 100 million. Yeah, so what happened with okay, so we got phosphors, right? If we recall, all these guys are blue pump LEDs. You guys went over that in sources, yeah? Blue pump LEDs. Okay, so we put this little phosphor slurry, right? These are both tunable whiteboards. This one has a little RGB chip in the middle, but it's got warm white and cool white. Which one's the warm white? The one on that side, one on that side? This side, why? How do you know?
Because the color is that.
It's like more orange, right? Yeah, more orange, more warm. Okay. So what happened, these are these little phosphors are made in a slurry, right? Imagine you got like a little. My kids had these like little color like syringes, right? And you could like impart color and make kind of like a stained glass bird. It's a lot like that. There's literally like a machine with like a little slurry that looked kind of like a, you know, like a hot glue gun, right? And it puts that slurry in there and then they cure the slurry. And the slurry has particles in it, which are the phosphors. And the particles of phosphors absorb the blue light, change it to other kinds of light. So these phosphors get damaged by heat. And obviously there's a shit ton of heat in these LED packages, right? So what was happening was the phosphor slurry, which was imparted into this little capsule, and sometimes these are actually more akin to what the LEDs look like in area lights, right? They have this like little dome, and sometimes the actual dome had a phosphor in it. So what was happening was like they got really hot. These are different materials, right? This phosphor slurry and the LED package itself, different materials. What happens when you heat up two different materials to the same temperature? You know the answer to this one. They could melt. What is another thing that could happen if they don't melt? What happens if things heat up? They could burn. Expansion. They expand. They explode. Now it has to be fail. We don't use the term explode. I was not allowed to use the term explode in a QA. HIDs non-passively fail. Actually, no, that was in Cooper. Yeah, so they expand at different rates. Like we have to deal with thermal expansion. So what was happening was these things were heating up and they were delaminating. The phosphors were delaminating, and you were seeing the LEDs without the phosphor on them. So blue and yellow make what kind of color? Kind of a purpley. Yeah. So that was an issue with the LED manufacturers, right? Not the luminaire manufacturers, because luminaire manufacturers like all buy their LEDs from like Cree, Lumileds, Achia. I don't know, there's a bunch of other ones out there I don't remember. So
they have they fixed that or?
yeah, they just have to throw new LED boards in there or replace the fixture. That's usually easier.
But the new ones, like.
The new ones shouldn't have as much issues, yeah. Yeah. Because I mean, basically, you know, obviously like the LED manufacturers were like, yeah, this is great. You can run it at this kind of thing. But the way that you, like, did you guys go over sources of like how they estimate the lifespan of LEDs,
Yeah.
right? Well, it's a simulation, right? You turn that thing on for like 6,000 hours, which is maybe like a couple of months, but it's not 10 years worth of stuff. And then all of a sudden you have those things being heated up in environments for several years and unexpected things happen. And one of those unexpected things was like, as you are expanding and contracting, turning on and off the fixture again and again and again, you have a differential expansion. And so the glue started to crack, right? And then the phosphorus delaminated. Does anybody on the like have like ever use like caulking on an exterior environment, and like after a couple of years, like the caulking starts to come apart from whatever you're trying to seal? Exact same phenomenon. It's just you have differential expansion and the things start to crack. So does that answer your question?
Yeah.
Okay. Any questions on bug rating? You guys have such great questions, by the way. You guys are like absolutely fantastic. 3 cheers. Okay, flood luminaires. We talked about collimation already, right? But you can, you make bigger, you use smaller sources, or you use bigger optics, you can get better collimation. Better collimation means I can throw my light farther down the road. But like we talked about ATOM do, it's very hard to get perfect collimation, near impossible, right? There can always be a little bit. So has anybody seen floodlights with like 3-degree beam spreads? Does it occur? It can. It's more common to go down about 5 degrees. You can imagine diminishing returns. It gets harder and harder and harder But you can do it. You can also throw hexel louvers on it, and that will get you even tighter beam spread. Right? So these, okay, so there's numerics here, right? And this is the way that these are classified as NEMA flood distributions, and they go like, you know, NEMA 5, NEMA 4, whatever, and they map to these kinds of they have a shape to them as well. So the NEMA classifications 1, 2, 3, 4, 5, 6 go to however the kind of distribution of that thing is. And an important distinction between NEMA distributions and like IES distributions is that NEMA only considers the 10%, what's called, I think it's called a field angle, if I'm not mistaken. Yep, field angle. Back to the drawing board real quick. If I have a distribution from my floodlight. This is kind of important because you will run into this, I promise. So I have my floodlight. There's a beam spread, which goes to 50% of the intensity, which might be something like out here. So this is like 50% intensity. And then the field angle, not the beam angle, the field angle only goes to 10% of the intensity. I didn't write a 10, Bill. Okay. So like, let's say we took a downlight distribution that was like this in a polar plot, and my downlight distribution looks something like that. Have we seen stuff that looks like that for like downlights? Okay. So if I draw my polar coordinates here. Okay, just, you know, ignore my crappy drawing. All right, let's say that looks something like that. Also, 50% of my maximum intensity is somewhere like here. So if I draw that out like this, and then I draw 2 lines through that, this angle is my beam angle. Now my field angle goes all the way to 10% of intensity. So my field angle encompasses a lot more range. The reason we want to use that in floodlights is important. This is a bad drawing. I did a crappy job here. It'd be more like that. Sorry, didn't mean to confuse you. Let's think here, right? So 10%, this is 10% of my intensity. My maximum intensity is down here on my polar plot. So anybody got an intuition is like why that's more important in floodlights than it is in like downlights? You're thinking.
You're trying to flood the area, right?
Yeah.
As much as you can get.
Yeah, exactly. It's like, do I have like most of my light here or just like 50% of it? I want like all my light right over there. So that's why they classify it that way, because it gives you a better kind of descriptor of like, where is all of my light going to be? If I say that my beam angle here, which is only 50% intensity, is like 10 degrees, that just means that like, it's not exactly 50%, but it could be like something like 50% of my light is in that 10 degrees. Well, that means I got 50% of my light outside there and I don't know where it is. If I want to floodlight that thing, I want like almost all my light to be on that thing. So I want 90%. It's not really 90%. I'm just using that as an analogy. But I really want like the vast majority of my light to be on that thing. So this can get you. It has gotten me. You may see an angle in there and they may not be super descriptive of what it is, right? So you may get like a really crappy performing floodlight that tells you the beam angle and not the field angle. Okay. Go for these from left to right. Big box retail, warehousing, assembly areas. Need a lot of light. I have big ceilings because I got a lot of heavy equipment and shelving. High bay is a good application. Maybe I use task lighting as well. A lot of assembly plants have like little areas where I can like put stuff together and I have some task lighting because the the, the thing is giving me like my general light, but I may need some fast light in addition to that. This to me is an airport, I think, based on that clear designation, which I always look at and go, I have no idea what that is. And then my kids are screaming, not kidding. I mean, airports these days are really, in generally pretty well designed. You got linears, you got troffers, you got downlights, you got cylinders, like you got coves and perimeters, right? Here's a nice example of a perimeter. This is looks like a rendered hospital corridor here. Why would I want to use a perimeter here instead of downlights? Patient, it's like looking right up, you know, as they're like, oh, downlight, you know, and just blasting in the face. Sorry to say that I've had that experience. But.
Good. Have some spot.
You might, I mean, you might have like, not a lot of light over on the side, that's a good point. So like in the interior environment, like maybe Lisa talked about, you can create an ambiance, right? Like if the walls are nice and bright, it feels more open, and I mean, I've always wanted to have surgery in one of those like video game, like dimly lit corridor hospitals where you feel like everything's gonna like, something's gonna jump out at you. That's really been my dream. Yeah. Exterior applications, right? You got flood lighting that's coming from these landscape lights here. You got flood lighting that's created a very specific ambiance, right? Like the Capitol building. I love watching the lights at the Capitol building here in Denver. Did I tell you guys the moth story?
No.
Did I hold it?
Alluded to it.
Yeah, earlier. Yeah, I don't really talk to moths. That's not real. But, okay, here's the story. So I worked at Lighting Design Alliance in Los Angeles for about 3.5 years before like in 2008, 2010, the housing crisis and the whole economy tanked and like all the projects I was working on put on hold. We worked on the AT&T building in Los Angeles, which is I think it's one of the tallest. I don't think it is the tallest, but it's pretty high up there. They have the top section of it is like super lit. It's like they want it to be like a beacon, right? It definitely doesn't meet code today, but when we designed it, it did. We put 2,000 watt metal halides that wrapped this like upper tier of the building and we're like facing in, right? So that thing looks like super bright. Okay, well, these are 2,000 watt metal halides. They get really hot. What insect likes light? Most of them in general, but yeah, moths like light for sure. So it just so happens that building is in a specific moth migration pattern. I'm not making this up. So these moths would fly into this building and they'd be like, oh, look. And come down onto this thing. What happens if you hit a moth with something that's like really hot? They explode? Yeah. Non-passively fail. Moths non-passively fail. Their wings started to melt. They would fall onto the top glass surface of the fixture that was aiming up, and they would just roast, like a moth barbecue. And every night there would be so many moths during this migration pattern. I don't remember what month it was. It could have been like March or April. I don't know. That you could no longer see on the fixture. Like they were like, huh, I paid, $1 million for this like super bright top of my tower. Why isn't it bright anymore? They sent the facilities maintenance guys out there and they're just covered in moths. They had to go up there like every 2 to 3 days and shovel dead moths off of the glass of these 2,000 watt metal halide fixtures. They had to call in like a professor of insects to be like, what is going on here? And he's like, oh yeah, that's the month the thing. It has like a migration pattern this during the month, and that's what those are. You're like, bummer.
So whose fault is that?
That's a great question.
Ownership.
Yeah, I don't know. They did change it. It became such a big problem. Yeah,
They
Of
do,
course.
millimoths do explode too.
they do explode.
Yeah, Denver's right at the top of the millimoth migration, and a couple years ago, it was really, really bad because we didn't have a cold enough winter. So they come from Kansas and across Denver, and they usually die in the middle of nowhere when it's cold, but it wasn't cold enough, so we had like a full force migration, which we shouldn't normally have. And there was like hundreds of thousands of them, and there was like hundreds of them in the gas fireplace, they had to make their way in.
Through the chimney.
Yes.
Yeah, nice.
They turned on and they were like pop, 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 they were like exploding like popcorn.
Do you have this on video? I feel like you should put this on YouTube.
They don't, but, yeah.
That's weird.
Yeah.
But you also have a moth story. We've got some good area lighting, right? These are high masts, right? High masts are just area lights that have a bunch of them super, super high up. We've got a couple of them like on the I-70 to C-470 transition there. Best Buy parking lots sometimes use these high masts. It's just kind of like their style. You can put one of them super high up and leave it be. In a super high windstorm, don't pay attention to the swaying. It's fine. Okay. Again, floodlighting here, right? So, I mean, something to call out here is just that, you know, we call fixtures certain things, right? We call them a downlight, we call them a linear or a cove or whatever. But as Lisa talked about, these are just fixture types, and there's no rhyme or reason of how you have to use a thing, right? There's certifications that say maybe this thing can't point up because of some heat dissipation or something like that. But lighting designers and you know, people that want to create a certain environment, these are your tools, right? There's no kind of like specific way that you have to use these products. Ratings, I'm gonna go pretty quick. ETL and UL and CRUS are like, you know, listings to say, is this thing safe? Does it comply to testing standards? It is a testing standard compliance rating. Right? Hazardous location ratings, sometimes important. You might get ratings for like sealed natures, which is the IP ratings, ingress protection. The first number is for solids, the second number is for water. It's pretty common to have like an IP, you know, 55, which is like just a general fixture, or IP 62 or 52, sorry. And then as you like get, you know, higher in as this number goes up, usually so does the solid, because if you can protect from water, you can usually protect from dust and debris, right? IP 68 is like basically submersion rated, right? The most common ones you worry about are like IP 63, 4, 5, 6, 7, and 8. Fixtures are also rated for maximum wattages. So this got kind of weird with screw-in LED bulbs, right? Because you design a system with a screw-in LED bulb that was like a 7-watt LED, and it was meant to replace like a 60-watt incandescent. The fixture can handle the heat of a 60-watt incandescent, which is only like 14% efficient. So now what you could do is, instead of that 7-watt LED, you could go and put a 20-watt LED in that bulb because the heat was the same, right? And that was a way that people were kind of like getting by the energy codes, because you put like 7 watts in there and then they just come in and put 20-watt screw-ins all over the place. That's basically what started the whole trend of getting rid of the screw base, because they were like, no, we don't want you to do that, right? We want you to like actually abide by the energy codes, for better, of course. A lot of times inspectors will require UL. Sometimes they're fine with ETL. Sometimes they're fine with CSA, Canadian Standards Association, like all sorts of stuff there. But again, most of these are testing standards. Any questions on ratings? Mountings. We're gonna blast through this. Recessed, it's in the ceiling. Surface mount, it's on the ceiling or on a wall. Pendant, it's hanging from the ceiling. There's a J box, right, that it's hanging from, but the fixture itself is still hanging. Track mounted. I always love these low voltage cable tracks. Like I always wanted to put like just a rod, you know, like a steel rod, like right in between it, and see if I can make it blow up.
Non-passive failure.
Non-passive. Thank you very much. You know, these could, you know, there's a specific thing called a tenon mount, right? So this is a post top tenon, and then this thing like slip fits on top of it. And you kind of put like some set screws. Super, super common for area top lights, and that means you can buy a pole from here and a fixture from here and whatever. 3 and 4 inch tenons are very, very common. I've seen like 2.5 inch too, but it's not as common. This is called a spreader mount. So you have this kind of thing in here that has set screws. You put it inside the pole, and then it kind of like expands, like friction fit, kind of like concrete sleeves. Arm mount. Sometimes you have an arm mount fixture in area lighting, and they also bring like a wall bracket adapter, so you can mount the same arm on the wall or on the side of the pole. It's very common in fixtures to ship mounting bolts for area lights ahead of time. They get like little J bolts and they put those in the concrete and they come bring a fixture on and bolt it in. And I always think it's like super fascinating to like look at poles that have these like just, you know, 1.5 inch bolts that are super beefy and they're, you know, only like 6 inches apart. I'm like, wow, man, it's like a lot of force on those bolts. You know, but engineering sometimes surprises you. Also the chairlift, you know, you're looking at like all the chairlifts that are bolted to the concrete there, and there's like a bolt like every 3 inches, you know, and I'm like, sure hope those things hold. Any questions on that? This is not a great, you know, image of in-grade mounting, but maybe you guys kind of get the point. A lot of in-grades fail. Just kind of how it is. They get water in them. A lot of times you'll walk over an in-grade, you'll be like, oh, there's a bunch of like water inside that optic, inside the glass, right? That means some seal has failed over time. It almost always happens. Which is really unfortunate because I think in-grades are fantastic. I think they're just like a great place to have lights and to create like ambiance without having a bunch of equipment. You're highlighting the architecture, not the fixture. Kind of like the equivalent of downlights. We got some bollards there, which you know, obviously you can get you know, retractable bollards. You can get drive over rated bollards. You can get drive into rated bollards. You can get just, you know, bollards that you can push over if you want to. And then we got floodlights and how, you know, landscape, I generally call stuff like this like landscape floods. You know, they're usually small, they're meant to be hidden. They're not like a bunch of light because you don't really need a bunch of light to highlight a piece of landscaping. My favorite is like the landscaping floodlights at the hotels that they put a bush right in front of, you know, and they don't really coordinate that. And so you're checking into the Holiday Inn Express and there's like this big floodlight that's just shining right into a bush, you know. I'm like, somebody thought that out well. Good coordination there. This is called a trunnion mount. There's also a thing called a yoke mount where it would like mount to the outside of the fixture, but gives you adjustability. It's always like the Holiday Inn Expresses and like the, you know, the lower end hotels and always have the big floodlights that are shooting right into bushes. I love it. And then have we been to the Gaylord Hotel out by the airport? If you guys go there next time you go or whatever, like check out all the bollards. They're all over the place. There's some that are just like this, and some of them like the actual aperture like fell over, but it's still, you know, up there. Like it's the maintenance on the light fixtures there has had a rough day.
With stronger IP ratings or.
Yeah. You can certainly do them. Yeah. Hydrel in the early 2000s used to have like the best in grades by far. They were fantastic. And what they did was they actually didn't try to seal the fixture. They had drainage holes right in the fixture. And then the installation note said that you had to essentially create a French pit. So you had like gravel around it and somewhere for the water to go, because I think the issue is just that if you are trying to like keep the water completely out of the fixture, then, you know, water is going to get in eventually. We've got the Grand Canyon. That's like the good example of water will do what it wants. And so you certainly can do that. They kind of stopped doing it because the installation, you know, only worked in a very specific way. But another way you can do this is you can encapsulate the whole fixture. That gets very expensive. But you can just have an entire fixture that's like encased in silicone. There's literally no way for the air to get into it. And they actually do this with tape light. They enclose the whole tape light in silicone. It's like one big. This is not exactly it. But this is kind of it, right? Like you can imagine the water could get into here. But if I'm just talking about this, there is no way water is going to get in that because the whole thing is just literally sealed. So that's one idea, but it's kind of it's hard to engineer. Yeah. Yeah, and they're also probably not that UV resistant. Who said that? Yeah. You can actually see that this one actually has some discoloration already. You look, and these ones, you know, are even worse. So UV damages plastic. Retrofit. Any questions on retrofits? Self-explanatory. Okay, we're gonna go fast through this. We already talked about a lot of stuff, but obviously, right, there are kind of like subtypes, right? Strip lights. You can have linear high bays, you can have linear low bays, you know. Again, I think like you can try to put names to stuff, but something I've definitely observed over the past 10 years of light fixtures is the light fixtures are just changing all the time, right? In here, they've got these like track mounted, you know, kind of, they're almost like downlight modules that you can put all along this kind of track. You can also put either like linear systems where you put like adjustables or downlight modules, or you could hang a linear from that system or whatever, right? They a lot of creativity in the fixture design, and LEDs really opened that up. And if you look over by the kitchen, in front of the lobby over there, there's that big fixture that kind of has like this shape that was called the canoe. It uses like LED OLEDs actually, which we don't use OLEDs anymore because they're, long story short, is that they're not a great light source. But they're very beautiful and soft. So that was like a new form factor. It's like, well, what is that? That's obviously a pendant, but then you got this acoustic thing over here too. That's got all these little tiny mini downlights in it, right? And so at some point, these names kind of start to not be super indicative about what it is. And so just be flexible in like how you think about things, I think. We're gonna go fast. Troffers. Downlight, you could have batwing distributions. If you're putting them in an MRI, what do you not want to have in your fixture? Specifically? What kind of metal? Steel? Is that steel? Yeah. Ferrous, that's the correct term. You don't have ferrous materials because ferrous materials are what? Magnetic, yeah. I thought it'd be really cool if you could have like an iron suit and then like jump and turn on like a super magnet that would like suck you against the wall. Has anybody ever played with ferrous fluid? Stuff's really cool. No, not mercury. It's kind of like a fluid that has like really tiny microscopic shavings of iron in it. It's called ferrous fluid. You can make it do all sorts of weird stuff. There's a video of like a guy who made like a music video, and he like messes with ferrous fluid as like part of the. It's like all these like weird physics things that he puts in there. I'll see if I can find it later. Strips are usually like not, you know, low bay or high bay type distributions, right? But strip light, aka everything has been stripped out of it that is not necessary. These are all typical high bays. We don't use these styles as much, right? We tend to use the UFO style because it's super cheap and they're all OEM'd out of China. Or you can do like the linear ones. Take a guess at how many different manufacturers have a product called LHB, linear high bay.
All of them?
Yeah, basically all of them. Yeah, it's ridiculous. I'm like, oh wait, which LHB is this again? You know, they can be surface mounted. They generally, you can build a lot of different distributions. In high bays, the distribution matters quite a bit, right? Because you got a lot of light. So if you use it intelligently, that can be helpful. We already talked about linears a bunch, but distributions vary quite a bit. A lot of linears, right? Has anybody experienced like shop drawings with linears? Yeah, got some head nods, right? Does anybody not know what shop drawings are in regards to linears? Or everybody good? Solid. Where's the emergency in the linear? Which one? Wherever you want it to be. Linear recess, same thing, right? A lot of linear families have like a recess, a surface, a wall, a pendant, right? A pendant can be direct, pendant can be indirect, direct, indirect, different distributions. ALW is really crazy and as far as like their kind of variances. This is kind of like, I think an interesting thing, right? On linears is like lumens per foot kind of deal. This is in a 4-foot section, but you know, lumens per foot in a linear can kind of be something like 500, maybe 1250 or 1500 per foot max. That could be split up or down. Obviously, the more you start to put down, the more glary that thing is going to get, right? Because you're putting a lot of light towards the user. 750 is about my recommended sweet spot, but. Now here's a pop quiz. You talk about luminance and metrics. Ooh, we gotta think. Luminance. Yeah, we did. What is luminance kind of a corollary to? What is it? Yeah, well, yeah, fair enough. Yeah. What is what do we generally in like layman's terms kind of call luminance? Starts with a B. Yeah, brightness. Yeah. So if I take 750 lumens in a 6-inch wide linear, right, that will have a luminance. If I take that same 750 lumens and I put it in a 2-inch linear, what's going to happen to the brightness? It's going to go up. Yeah. So which one of those has higher luminance? It's the smaller one. Exactly. There's a relationship there. Linear strip and tape light. I don't think anything needs to be kind of really discussed there. Sometimes, these are more like floods, or I should say like grazers. Sometimes they're more, they can have asymmetric, right? So you put it against the wall and it kind of like grazes the wall. Some of those, yeah, this looks like very much like the same profile, right? Here's like a cove picture. Kind of an architectural detail there, right? You can hide that thing. Y'all good? Is that chair not comfy? We get you a new one.
No, I have scoliosis, so
Oh,
I
okay, sorry.
a lot.
Pop away. Okay. Perimeters. This is the stereotypical perimeter right here. That perimeter light. This to me looks like a rendering. Does it look like a rendering, anybody else? Downlights. You could have adjustables, right? You could have aimables. You could have a wall wash. This is like the downlight wall wash. You can tell that it's not a great wall wash, right? It's hard to get a wall wash distribution out of a circle. Taking the circle, trying to like point all of it towards the wall. It's pretty hard. So if you ever see like a really good circular wall wash, like a circular aperture wall wash, they got a good optical person there. Or they paid a good optical person outside. Okay. Decoratives. Anybody have an idea about what that thing costs?
Awesome.
Not quite, yeah. The max size of the artichoke's about 25, something like that.
How big is that axle?
Oh, it's big, yeah, about like yay. It's a big deal. Big artichoke, yeah. Somebody was eating artichokes. Yeah, buddy. Okay. There's a lot of different ways to make luminaires. It's the whole deal, right? You can injection mold parts, you can stamp metal, you can roll form metal. That's a YouTube rabbit hole. Have fun. Okay. We've already talked about a whole bunch of this stuff already. Areas, you can use them in parking lots and streets, bollards. This is nice, right? Having a couple of just general nice kind of these are definitely still area lights, right? But they have kind of like they have a luminance component to them. They have a brightness to them. They're not like flat utilitarian where they're trying to shove light to the ground. They're intended to glow, right? Where are areas that you've seen that kind of stuff? Hospitals, like on the outside of the hospital? Yeah. Where else? Park? Yeah, where else? What? Campuses? Pretty good list. I've seen them on bridges too. Sometimes piers. I walking down a pier, like the Huntington Beach Pier. Oh, look at that decorative post op. Sorry. Okay. Wall mounted luminaires. This looks like some sort of occupancy, like little step light thing. Wall packs, more decorative wall deals, more industrial wall packs. We used to call this thing a jelly jar, right? You just stick a light bulb in it. Obviously, you can infer the optical characteristics of each of these, right? Garage mounted luminaires. This was a really, really interesting garage luminaire if you've ever seen that thing in person. I think I've only seen it once. I think it was a Cooper product, although don't quote me on that. These are the nice ones. You go to DIA and look at the parking lot. The fixtures are not nice, not good looking. Floodlights, talked about that a bunch. Pendants, accent lights, landscaping, step lights. Any questions on all those guys? Path lights, etc. Okay, luminaires complete.
Sorry, I have so much questions. Sorry, everyone. Okay, so let's say like you're in a parking lot and it's a great parking lot and the lights.
It's a great parking lot.
It's a great.
It's like the best parking lot.
It is the best
Okay.
because it's for an airport and all of the parking spaces have individual little lights that turn green or red.
Okay, cool.
Is
They're probably
that just
cost.
occupancy? Oh, they have like an internal occupancy sensor?
Yeah, sometimes they have like a little laser guide thing right above the parking spot. There could be like several ways to solve this, and I'll just be completely transparent. I don't know how they always do it. I'm guessing there's more than one way. And you know, if you go and park your car under that thing, under that laser, right, which is calibrated to say like this should be a distance of like 10 feet, then if you know if your car is there, it's like only 2 feet to the like little laser guide. They might have some sort of like image recognition too, where there's a camera. But fundamentally, those like, you know, there's either like green lights like in the pavement, or they're like above in like a row, and it's either green or red. Just supposed to give you an idea of if you can park there or not if the spot's full. Because I got a truck that's way too big that's parked down there, and I hate parking at DIA. I always have to go like way out. Yeah. I've seen that at some place that has like a restaurant down near DTC. It's like a parking garage. Yeah. I'm not sure I answered your question there, but your question was like, why do they do that?
Yeah, I just like them.
Yeah,
I think all parking lots should have them.
yeah, it's super nice if you know that there's a spot down there and I can go park there. Yeah, it'd be even cooler if, well, actually, so companies are trying to do this with phone apps too, where you would like be able to see on a map like where spots were open, and they would just feed that directly to you. Like you had your DIA parking app or whatever, and it could be like there's spots here.
Jericho Mall.
At the mall, you can do that at the mall. Yeah, do they have that?
Yeah, they do have green or red, so if it's red,
Yeah.
it's full, it's green, you can go.
Yeah, yeah. So, you know, what I really want is everybody to be looking at the app about where they're supposed to drive when trying to be in the parking lot, you know? Like, I think that whole idea was kind of a bad idea, and I think the green red lights are like a lot better. You can even have it at the aisle too, right? You can just say, oh, there's some things on this aisle, and then you go down the aisle and you find it. Bathroom break, stand, burpees. Anyone? Anyone? Bueller? Actually, funny thing, in Ferris Bueller's Day Off, the professor is talking about tariffs of the 1930s. Yeah, I thought that was pretty weird. People used to tell me that I looked like the dude, his friend, Ferris Bueller's friend. Yeah. Yeah. Okay, how's everybody doing? Get some movement going. Is it getting hotter in here, or is it just me? Okay, it is getting hotter. Let's do this. Ooh, lunch. So here would be my recommendation if you guys want to do this. I would say let's like take 10 minutes to grab lunch and eat it in here. And then we'll just keep moving, and then you guys get more time to go the day.
And we'll be in the video while.
I can turn off the video. Yeah. I can't control the owl like moving its like little camera that does that on. So you guys want to do that? Do you want to eat now, or you want to just wait? Let's eat.
Let's grab lunch.
She wants to stand. She wants to get back. Do it.
Can you share your screen again? For some reason, it stopped sharing.
I think that's because I was sharing the. Appropriate for the box. Yeah, it's there.
Okay. I'll make sure that's working.
Yeah, no
But yeah, it just like flashed all of a sudden. It's like, oh, no. First, it's because it's school.
Sorry, yeah, it's Zoom is kind of tough sometimes.
Yeah, it's not my preference.
You win. The certificate will show up. You might have to ask. Yeah,
Should be good.
you might have to ask. It's all very usual about shot, but yeah.
Sort of good. My sister has celiac, so it's interesting. Trying to go out to eat with her.
Yeah, my wife's, I call it great aunt.
Okay.
It was like her grandmother's sister,
Yes.
died from accidentally eating gluten. She had celiac disease. She got a bunch of internal bleeding and was kind of like old enough that she just didn't realize what was happening.
Yeah.
And they did the autopsy on them, and they were like, her intestines were like bleeding, literally.
Oh,
Like, how sad, just because she ate some gluten.
Yeah, it's really horrible. Yeah. Terrifying.
I just get like a lot of stomach pains,
Yeah.
So it's usually, it's not the end of the world, but.
Yeah,
I
it's
do
not
try
too
to
bad.
avoid it.
It seems to affect everyone differently. One of my friends, she gets migraines.
Yeah. I think it's really just an inflammation response, right? It's like,
Yeah.
what's going on in your gut?
Right.
It doesn't like that protein. You're getting an inflammation response. And I think people respond to impact by different ways.
Yeah.
My son has A1 protein allergy. It's one of the casein proteins in dairy. So most dairy just comes from like Jersey cows, right?
Right.
They have A1 casein protein and A2 casein protein in the milk, and they also have like the whey proteins.
Yeah.
There's kind of like 3 major types of proteins in there.
Right.
He's allergic to the A1, and so they now have A2 specific milk that doesn't have the A1 proteins, which come from cows, which have kind of like been selectively bred to not have that protein. And the funny thing is that like humans, sheep, goat, buffalo, like basically anything else you can name does not have that A1 casein protein. It's only those cows. So it kind of makes sense that generally people don't do that well with it because we're coming off of like human milk.
Right.
And so he gets like rashes like all over his body. And they actually, it was really hard to diagnose because they usually occur about 4 or 5 days after he has it. And it takes a long time to go away. So you can have dairy like just one, like the long glass of milk.
Right.
Takes 3 or 4 days to come up, and then he has it for like 2 weeks.
I was gonna ask how we found out about that, because I feel like that's such a specific
It was
thing,
really
and
hard.
not a typical allergy.
Yeah. Yeah, it was hard.
Yeah.
Have you on camera?
Yeah, we do the camera thing.
Make sure it's working.
Yeah. All right, we're gonna turn the video off. Well, we're eating food. This thing is so funny looking.
I know it is.
Or it's a little bit un-PC. You remember the fembots, Austin Towers? Yeah.
It's the 90s.
Yeah, what's that?
Is it the 90s?
I don't know when this came about, I know it was like this, like that was the kind of intended, hanging thing, but. Yeah, I had all these like samples, like light picture samples, right? And I mean, TLA in the basement here has like a whole room of fixture samples.
Wow.
And at some point, you're like, these are no longer applicable, right? The manufacturers don't want them back, so what do? Like, you always
Store 'em.
roll them away,
Now they sit in your garage.
Well, this is the only stuff I have, but
You can save it for like 2050. You
Yeah.
show it to people.
It's the history.
It's like, hey.
check this out. This is a Wi-Fi bulb, like those, standard stuff you buy at, anywhere. And I cut the top of it off. So you can see kind of what's like actually in those things.
Is that the Korean one?
What brand is that on there? Oh, that's a TP.
I have the Korean ones like that in my office. Even though I work in lighting, I don't like lighting.
Yeah, you can control with your phone or whatever. Yeah. Maybe like how much crap you can collect. Yeah, well, we've got everybody, let me know. Not bad, borrow this one. Trippy stuff. Thanks, sir. Anybody else want to see a Wi-Fi ball that's gonna open? Yeah. We grew a giraffe, we grew a volcano to make water. The logic seems so solid. Yeah. That one is RGBW, I think. All right, it's 12:10. We ready to move? Okay. I know you all are eating, but again, feel free to interrupt me as you feel appropriate. Clarification questions, just let me know. Peter, don't fail me now. A review. Okay, light is blank. That is capable of exciting the retina. Anybody remember? Say again?
Photon between wavelengths 380 to 780.
Nice. This one says 770. I wouldn't even discount that. The first slide may have said 780. That's how kind of fuzzy we are on it. Yeah, and it is photons, right? And the kind of the hardcore definition is radiant energy, right? Which in this term, you know, is photons. It's good stuff. Which type of electromagnetic radiation makes people into the Hulk? Yeah. Do we use long radio waves for anything? Radio? What's that? X-rays?
No.
Long waves, yeah, super long waves. Where do these occur mostly? Space. Space. Okay, can we name these four components? The source? Yep, also called the modifier. Nice. You got the interpreter, right? That's the brain. The collector is also known as the receiver. Good memory, everybody. Nice job. Okay, so vision and perception. Right, lots of things influence our perception. Our visual system takes in a lot of information, in a lot of different dimensions. Visibility is influenced by these things plus what? Contrast is one of them. Very nice. Be able to read my text, I need contrast. One more thing. Some people can't see it very well. Color. Right, contrast and color affect visibility. This is a good summary, but if I said that the light level was very low in this parking lot, what of these three vision type columns classifications would we be in? Think parking lot. Maybe look at the color sensitivity row. Yeah, bingo, nice work. Mazopic. Right, I can see the color of the cars, right? Unless it's really, really dim. And then maybe I can't see the color of the cars anymore, and that is when I am fully scotopic. And you know, I can't see any of the color vision anymore. My recollection memory of being 100% scotopic was when I was like 12 years old and going to TP a friend's house. My buddy and I were like, it was like just moonlight, right? That was it. And then photopic is cone dominated, which gives us our color vision. Examples of contrast and brightness. I don't think I have the fun, you know, slide over thing in this one. I was on the other slide, but obviously the okay, so this is really interesting. We'll bring this kind of full circle into what's above our heads right now. So, not intended to be a trick question. Do you think that there's anything different about the LEDs in one of these cells or another that is making it gray? Do you think that there are such a thing as gray LEDs? It's a good face. Yeah, no. Right, so what is the perception of gray? Brightness, who said that? Very nice. Right, what's I got a whole gray scale here, right? And all it is a reflection. So one of the really funny things about designing this fixture was that we could only make things appear gray if there was something that was brighter next to it. Otherwise, it just looked white, right? Now, obviously, this one looks gray because these are all the same, but we have some, you know, some stuff next to it, right? If this room was all very dark, these ceiling tiles might look white instead of gray. And especially if we put light onto them, they're definitely going to look more white than gray because they're going to be more lit up. So white is a reflection of like all the colors at the same time, right? And the perception of gray is just like, is it lighter, or I should say brighter or less bright than things that are in my vision? So this kind of expands our scope of like vision and color into what we are perceiving in our interpreter as a whole, right? The interpreter starts to make these kinds of things in our brain.
So gray is just a contrast of brightness between white and black. See around it.
Yeah. Yeah. Like it's really, I mean, contrast at its core would be how much light's on this thing versus how much light's on this thing, or coming out of these two things. And the gray is the perception of less, really in relation to something else. So getting these colors, now this is a fun one, getting these colors to appear the same. As we increase the light level or decrease the light level, keeping those colors to be mostly the same was very hard. And we didn't need to do a perfect job, you can probably tell. Because we actually had to build an algorithm that changed the red, green, blue mix as the fixture dimmed down to keep the picture looking the same. That's why I know so much shit about color, because I had to go through like, I spent 3 months trying to figure that thing out. It was really cool. Okay, let's see.
right? Your environment can change a lot about your visibility and perception, right? This is, pretty nice. I think that I'm totally fine driving down this road or walking down this road. But we've got wet streets, right, which are gonna create glare as the street lights reflect that stuff. So that's gonna impact our visibility. It's how am I adapted, right? Did I just come from an area that had like a lot of light, like a city, and I'm now like moving into like more of a countryside with less light. We talked about if I drive into a dark tunnel and it was daylight, right? This is going into Eisenhower Tunnel at like 80 miles an hour. It's super bright outside. And then what do I need in a tunnel? I need a lot of light at the beginning because I'm adapted to highlight environments. If I were to just kill all the lights in that tunnel, then I'd have a big problem because it takes time for the visual system to readapt to a new light level. And that's why you guys recall when I said, like, when you go into Eisenhower, you'll see more lights at the beginning, and then the number of lights will kind of fade off as you go down. It gives you time to adapt. If you have like a high speed of movement, do you need more or less time to see that thing? You need more. What do you get if you're moving really fast? Less. You get less time. So what do you need to do to compensate for that? More light. Kill it. Right. This is called out well. Multiple perspectives. Okay, so like cognitive load here, right? I'm in this, downtown city area. I'm driving. There's lights on the sidewalk. There's lights in the street lights. There's area lights coming down. I got people walking across the sidewalk. I got bikers that are either going here or they're passing me. I've got this courier dude who's like on amphetamines and he is riding so fast, like he's weaving in and out of traffic and he's like, YOLO, I got this. And then you got that guy on YouTube who's like the rollerblader dude that's doing like 25 miles an hour and just does not really care about anything in New York City and is totally killing it. You know what I'm talking about? Yeah, you see that guy? Yeah, he's good. Amazing. So those are like cognitive loads, right? You're trying to balance mentally all these things that are happening simultaneously, right? So people do, when they design stuff like this, they actually do need to think about it, right? Okay, so transient adaptation means, right, I am transitioning from one area to another, and the transient aspect is that it's temporary, right? I am adapting, like as I drive into this garage state or I come into a lobby that has like a lot of daylight, I'm only going to be in that area as I walk through the lobby. It's a temporary environment, right? So you have to think about what you need there. And the entry to the tunnel is a perfect example of that. Okay, we got CCT up at the top, right? Higher color temperatures are more blue, also known as what? What do we call that sometimes? Cooler. Does anybody remember the black body? What does 10,000 K actually mean? Or what does 2,700 K actually mean?
Kelvin.
It's Kelvin, right? It's temperatures in Kelvin. Temperatures in Kelvin of what? What? Char? Chalk. I don't think so. I'm not sure.
Yeah. I thought that was a temperature thing. Actually, I think this is.
Well, it's anything that burns,
So,
right?
the brightness,
Is it what?
the 27K is the kind of the brightness, how like you can change the temperature of the.
You can change temperature. You might get more or less like light out of it, but it's specifically the correlated color temperature. What was the chalk thing? I think you're on something, but go ahead.
Oh, I'm sorry. I was just thinking more like the amount of blue.
Yeah, for sure. Just so let's think about like a flame that's like a nice big flame, right? You got a lot of different colors in that flame. There's some like nice oranges and yellows kind of near the tip or the outside of the flame. And you got blues in the middle, right? Which part is hotter? Blues. Has a higher correlated color temperature. We just use correlated color temperature to mean essentially tint, right? But this comes from the black body radiator at its fundamental physics level, and it's how much, like, what is the temperature in Kelvin of that black body radiator? Usually we simulate black body radiators as like filaments that burn.
or a flame, something of that nature. I have not heard the chalk one before, so it could be you got it right and I got it wrong here, but
I can't find anything.
so then, now, when we say correlated color temperature, there's a human aspect of this. Right, does everybody remember I talked about this very briefly in this stuff where we have this line, and this was from humans. We asked a bunch of humans, what color does this look mostly like? This line here is called the black body curve. And so everything on this is like the exact chromaticity that when that thing is on is emitting energy, what the color of that thing is. And we can have, multiple, we basically create like, perpendicular lines. Anything on that perpendicular line is the same color. So what does that mean? I could have two fixtures from different manufacturers that use different LED suppliers that both say that they're 4000K and it could look different, right? The same thing. So generally, I think my recommendation was like, if you have different fixtures, you want them to be like illuminating different things and not directly next to each other. The really crappy example of this is like long coves in airports that they use fluorescent lights on, and you'd see like the different bulbs that they put in all that stuff. That kind of thing can happen, which is very annoying. Ever remember these 99 different color samples? What was that about? Color and who and what now?
It's basically, what percentage of those colors actually show up through themselves when the light is.
Very well summarized. Yep, exactly, right? So these 99 were about the TM30 color rendition metrics. And the CRI stands for color rendering index, rendering rendition, right? Same word. And so in CRI, there was like 14 colors, right? And most of them were kind of like pastels, if you guys recall. And there's a lot of colors in the world that are not pastels. So TM30 was intended to replace CRI, and it was meant to do so with a lot more colors to be more representational of the colors that we see in the world. I don't think it's been well adopted, right? Even though it should be. The manufacturers are good at manufacturing things, not necessarily documenting things or adopting new processes. Objects have no color. That's a weird statement. Why is that true? True. They reflect light. And also color is what at its core? Do dogs see the same color that we do?
No.
Do moths?
Mhm.
No. Right? It's perceived. Very nice. Always bugs me. I rotate it and I forget to save. This is supposed to be a multiply, right? Take my reflectance and my source and multiply those two spectrums, spectral power distribution and reflectance power distribution. I multiply them together and I get my result that comes into my eye. So source, modifier, receiver. Cool. Here's the first 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Here's the first 8 colors that were in CRI. Everybody remember R9? Anybody ever heard that? Like, yeah, CRI with a CRI of 82 with an R9 of like 91. And you're like, cool, bro. I'm from California, don't judge me. Yeah, you can see these colors like are not that great. They're not super helpful for like a lot of the colors that we see in the world, right? This is a much better representation. We have tints. My daughter taught me this. We have tints, right? We've got shades, right? We got all sorts of stuff that are much more indicative of how things will actually work. So this is great. TM30 is great. It's unfortunate that it's not well adopted. Talked about CCT. Now, these are the same rooms, obviously, with 2 different sources which have high rendition. You can have high 5000K rendition and high 3000K rendition. But even with the 2 of those difference, you will perceive the space differently, right? Because they have different percentages of energy and different
parts of the spectrum, and therefore you will kind of make things pop more. Like to me, the biggest thing that comes out here is that the floor here has less reds, right? And then the walls in here are much more crisp white, right? And again, crisp is like a subjective term, right? But we try to find words that kind of mean things.
The space looks bigger. Is like
You think it looks bigger? I can see that. More crisp white things tend to, you know, feel more expansive.
Less shadings, it's less dimension.
Say that one more time.
Less shadings, it's less dimension.
Yeah. That is true, isn't it? Yeah, I see a lot of scallops in this one. That's probably, you know, and look at the shadow here. Nice observation. Like this stuff matters or something. Cool. Tunable light. Okay, so you brought up 2-channel drivers. I'm happy to talk about drivers and whatever else you guys want until you know, the one of us goes blue in the face. No pun, the 6500K. So this would be like a dual channel driver. This one, you know, a lot of companies make stuff like this, right? But basically you put 2 different sets of leads, a positive and a negative to your warm white chips and a positive and a negative to your cool white chips, and you can, you know, you're driving them independently. It's kind of like you have 2 drivers in one box. It's just how it is. And you can create spaces like this. If you remember in light and health, what was like a class of people that really benefit from like tunable light and varied light levels and stuff like that?
Alzheimer's patients.
Yeah, the elderly. They don't move a lot, don't go outside a lot. They're kind of the ones that benefit from that stuff the most. And man, are those assisted living communities expensive. Unbelievable. Like, really? This is the lighting you guys got in here? Like, this is the architecture? Like, the carpet smells, guys. Come on. Okay. Any questions on color terms here? All good? Okay, so I'm gonna go from right to left. If I've got my building facing this way, if you guys recall, I think it was a Thursday we discussed this, right? What are some issues I need to deal with here? I've got a big side of my building that faces west and east. What's gonna happen? A lot of sun. When? Yep. Yep, exactly. So the sun's going to be where in the sky at those times? That's when it is. Like, where is it going to be in the sky? Right. On the horizon. So what's that going to cause to me as a person in this building? Glare. So I got to deal with that glare. I got to do something there. Right. What are techniques I might want to do here if I have kind of like a large area of my building that's facing north and south? Large surface area. Blinds. Yeah. Right. What else can I do in that situation? I can harvest the daylight. I got a whole bunch of techniques to bring that daylight into my space, right? And what's a benefit in general, right? Not always throughout the entire part of the year, but if I have like a large south facing or north facing, that's north, that's south, if I believe, if I have my orientation correct, give or take, it'd be like that's north, something in that area. You know, but if I'm on the south side, we're here in Colorado at about 40 degrees, give or take, maybe about 39 where we stand now. Is the sun going to be like low? Am I going to see it directly out of clear window at noon? Probably going to be up high, so that's nice because I don't have to deal with as much glare issues if I orient my building that way. But you're correct. Like I may want to harvest that stuff. I may want to use one of these techniques to offset my electric lighting. This is probably, I think, you know, somewhat of a north, maybe northwest a little bit facing window.
But I don't really need a whole lot of treatment there, and you can see they don't really have much, they have this like little fritted, you know, kind of line that just maybe just cuts down a little bit of the total light. But in general, that's gonna be nice. No treatment on this clear story window right here whatsoever. Pretty nice. So I've got all my techniques. I've got this, whatever this room was that I remember we talked about that had like the boom box on it from like 1998. I've got shades and fritting. I've got light shelves and shades. I've got some sort of, you know, like, I mean, if you think about your hex louvers, right? Essentially doing a very similar thing, right? They're trying to block angles of light. This would be my curve of, you know, daylight harvesting. It'd be, what can I do to my electric lights as I get more or less daylight? My favorite, the compact fluorescent. Any questions on these guys? This is an interesting slide. I don't think it got brought up a whole bunch. The source versus the lamp. We talk about that? Does it matter?
Bob hit it pretty hard.
If it what?
Bob hit it.
Bob hit it hard. Okay, cool. Yeah. You know, it's kind of an interesting thing. Is the lamp the source? Technically, no. Do they kind of, are they basically the same thing in a lot of cases? Yeah, they are. Any questions on that stuff? Feel free. The 86 different types of lamps. My favorite. So what does a par 30 mean? Swear to God, this is gonna be one of those like flip deals, you know what I mean? I'm just gonna go and eat it. Say that again. Close. Any other guesses? She's close. Second guess? Final answer, fun friend? Hint?
We're busy right now.
Okay. So the P is parabolic. That is true. And the 30 is, the aperture is 38ths of an inch wide. Because that makes sense. Yeah. A19 is a A-type shape, 19/8 of an inch wide. Yep. BT is bulge tube. F is flame shaped, G is globe shaped, T is tubular shaped, R is reflect, I think it's just reflector. R is parabolic. Again, T is tubular shaped. Again, this is also parabolic, P64. The AR is aluminized reflector, but again, 111 is 111/8 of an inch. This is actually my favorite lamp of all time. MR was metallic reflector. Most of that stuff doesn't matter anymore, but you still can find a lot of this stuff in LED form.
I know we can find the G25, and I don't see E26 here, and the A19.
What does the E stand for?
It's the base, the.
Yep, there's like an E26 base. Yeah. You also have an E-type bulb, so the bulb could be a E15 or it could be ED15, or it could be ET15. It goes on and on and on. I just did a project involving all this crap, so it's all fresh in my mind. E stands for elliptical, ET stands for elliptical tube, ED stands for elliptical dimple. My God. Okay. Photometric terms. We're doing good. We're halfway done with this. And I'll aim to get you guys out here before 1. Cool. Okay, luminous flux. Talked about this already. Luminous intensity is in candela, right? I drew this diagram over here. More intensity equals more light in a specific direction. intensity is not just lumens, it's lumens in a direction. If I put more lumens one collimated way, I get more intensity. I could take all the light, let's say this is 1,000 lumens. If I squish this distribution to be more like like a spotlight, I get more intensity out of the same lumens. Does that make sense? If I took the same 1,000 lumens and it was a 10-degree beam spread, but now I want to put a diffuser on it, kind of like softens that beam spread out to 20 degrees, I lose my intensity, right? So intensity and beam angle and lumens are three triangles of the same, or the three facets of a triangle that defines some aspects. Does that make sense? Intensity is important. Illuminance is on what? A surface, very nice. And then what is it on a surface? It's not like it says it right there, but how much light, how much lumens? Yeah. And it's specifically flux, right? So it's a rate of light coming onto a surface. Reflectance, easy one, we put in one number, percentage of all the light that hits it versus the percentage of light that reflects off. I'm sorry, versus the percentage of light that reflects off, yeah. Excidence. What is that? We already used the term E for illuminance because illuminance starts with an E, and excidence obviously starts with an M. Obviously.
Is absorbed and taken away.
Close. That would be like kind of the reflectance percentage. But if I were to take my reflectance percentage times my illuminance, check out the units here. Exit. How much light's being reflected off per square unit. So the light that I see off of this table is the excidence or the illuminance. It's the excidence, bingo. So we always measure, why would we measure the illuminance? Why would we tell you I want 30-foot candles on this table if that has no idea, if it doesn't relate to like what I see? It's not a trick question, but it's not an easy one. Any ideas? It takes those, go ahead.
You don't know what what table's gonna be made out of or what it's going to be, so you can't calculate the reflector and say,
Yeah, it takes the table out of the equation, right? It just says, hey, I'm gonna give you 50-foot candles. You wanna make black tables? Go for it, right? Now that'll give you a lot of contrast on your paper. So you may be able to read that paper like nice, right? But, a lot of times something that this does happen quite often is you like design a space and somebody goes like, hey, I'm only getting like 10-foot candles on my work surface. Like why, this was supposed to be designed to 30. Right, what do you think may have happened in that space?
Materials used.
Say again?
The materials they use.
Could have been, yeah, exactly. But where? Right. All this light's bouncing around the room constantly. This table is not just being lit by that fixture, it's being lit by that wall and that fixture. Stuff bounces off the floor, goes back up to the ceiling, comes back down. Right. That's why we calculate and goes like it's a progress bar because it's literally going bing, 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 right, and calculating that thing. Okay, luminance. This is the hardest one to really, I would say, understand mathematically. It's the easiest one to understand conceptually. How bright is that thing? I'm going to look right at it. It has a direction, right? And the luminance is the surface area. So let's pick like one of these like mostly homogeneous trophers right here, ignore the lines. That has the same luminance across the entire surface because it's all the same brightness. Does that make sense? This one, right? So this one, the luminance is changing. Each cell is changing its luminance. And what's really happening there is I have a bright surface that is emitting light, and luminance is also directional. Because it's candela. Candela is intensity. Intensity is in a direction. If I have a flashlight, which I don't, you guys can imagine I shine a flashlight over there. That flashlight contributes no intensity, right, over that direction. So intensity is directional. Luminance is directional. Okay. So you could also imagine
sometimes my analogies start to get a little funky here. Right, we have no luminance or very little luminance coming from this shade into this space because it's directional. If I were to go to the outside of the building and I look at this shade through the window, that shade has luminance that direction because there's light coming off of it. Because luminance can also be a reflected light. That makes sense? This has a luminance, but it also has an excidence. So on this table, what's the difference between excidence and luminance? Say it again.
The accident is how much of the light is coming out,
Yep.
and the lumen is the surface of the light.
The lumens is the surface of the light.
The lumen is how many is absorbing.
Yeah, that's the reflectance, would be the how many lumens go onto it versus out in an area. This is a hard one. This is why luminance is the hardest one. So excidence has no directionality. How many lumens go onto this table? How many lumens come off of this table? Excidence is how many lumens per unit area go off of this table. If I want luminance, I have to now consider direction. I have to now consider where that light is coming off of in what direction. Does that make sense? Okay. It will only take 20 years for that to make sense. Don't worry about it. Everybody familiar with polar plots? These are actually fairly intuitive, right? In optics, we use a thing called Cartesian plots instead of polar plots. Because this does a nice job at hiding some information that you want to know. But for the most part, you guys don't need to do that. That's just when you're designing optics. Unless you're going into optics. In that case, have fun. Okay. Also pretty good here. Now, something in photometry that's a little bit more nuanced. Do you guys remember what these lines mean? Yeah, they're azimuth angles or like horizontal angles, right? So this would be where the peak is. Again, we don't have any linears in here, so this is kind of hard to like imagine. But you know, like the batwing distribution, if I have a long linear that like runs right down the middle here, I have a batwing distribution. Which way is the batwing kind of pointing? Yeah, exactly. It's like that, right? So now if I go like this, right, I may not have a batwing, I may just be more diffuse. Right, and then my ballet move, and my batwing expands right out to the outside. It's a shame we didn't have it on video. So, obviously, you're trying to take three-dimensional data here, right, which is the ballet move, and you're trying to represent it on one page, a 2D thing. So that's how we collapse the 3D into 2D. Right? We do different things. That make sense? Okay, we got horizontal luminance on a table. Ooh, the angle of attack. I don't think I've ever used that term in lighting. Do you remember the inverse square law? Don't worry about angle of attack, just remove that from your brain. That's only for fighter jets, which is a much more exciting people. Especially since we're spending how much money on the F-37? Inverse square law, remember that? No? You want to go over it again? Right. So let's say I got this troffer here and it puts 20 foot candles on here. What happens if I move that troffer up 10 feet?
And less candles.
Less lumens on the surface, right? Why is that? It does spread out. Very nice. That is actually the core reason, right? But how do we approximate what's gonna happen here? I don't know if you knew how good of a reason that is, actually. That's a very, very hard concept, right? I have this inverse square law. As my distance increases, it spreads out more. And the way that happens is with a square. So I take the distance, maybe this is 6 feet, 7 feet for that. If I had it at 17 feet, I square the distance on the bottom, and therefore I get a lot less foot candles. Light loss factors, things we don't really use anymore. Has anybody done light loss factors in the past like 2, 3 years, 4 years, 5 years? Not really. If you want to do a good job, we still get luminary depreciation, and we definitely have source depreciation.
The way I used to do this is I just multiply by 0.8. I'm done. I'm not saying you should do that, I'm just saying that's what I did. Okay, so we got luminance meters. Has anybody ever seen one of these or used one of these? I wasn't able to borrow one for this class. I used to be able to borrow one, but the buddy that I knew that had this, it broke. These cost about $10,000. And so they don't have one anymore, unfortunately. But this has a luminance meter. This is where you put your eye, that's where you aim it. Now, why do I need to put my eye on this thing, and why does it have a trigger, and why does it look kind of like some weird, funky, like laser photon gun? I'm harping on this. Because the luminance is in a direction. So I gotta point this at a thing to know that it's coming back at me, right? Kind of like a camera, right? It's kind of like you got your little camera like focusing at a thing, right? Light in that direction. So when we take pictures of things, we're taking pictures of the light that's coming off that thing to us, aka the luminance. A color spectrometer. This does the same thing as my, like 10-foot candles, but it just gives you the color information as well, right? Then everybody's seen the illuminance meters. Okay, thinking about controls. What lights are you controlling? What do you want the lights to do? Well, I want them to like change over time and like do a bunch of weird stuff in the room. How do you want to control the lights? We just did control, so right, don't need to spend more time here. Passive infrared, PIR, right, is really good for what? Sensing. That was kind of a broad statement.
Sensing people.
Yeah, sensing people, right? What else? Raccoons.
Yeah.
The ultrasonic adds people that don't move, right? Because the PIR stuff, like if I just sit there, right? I'm not moving, I forgot about lunch, I need to go to the bathroom, but I haven't gotten up in 3 hours. Right, you don't move, the passive infrared won't catch you. Occupancy, vacancy, we just talked about that. Any questions on occupancy and vacancy? We'll look at 10 minutes. Okay, balancing lighting quality, right? There is the architecture. There is the architect that says, I designed this amazing building. I want you lighting designers to make this building look amazing day, night, all the time, right? There's the economics. How much do you want to pay for that good optical control? How much do you want to pay for those nice fixtures? Is it easy to install? Is it hard to install? Is the drywall going to look good on that trimless downlight? Do you have a good drywall contract? Because you should. Okay. Has anybody ever seen a bunch of like trimless downlights that like kind of go down a line and they kind of just move a little bit? That was so frustrating. The other thing is that sometimes you can rotate them. Sometimes like they're in the right spot, they're in a line, but they're like rotated. I worked on an attorney's firm that paid a lot of money for a really nice lighting thing. They were so pissed at the contractor installing the lights. They were like pissed. Yeah. They had to like rip out all the drywall and redo all the lights. Pretty gnarly. The electrician had to pay for it because the drywaller basically said the electrician had not installed them correctly. So electrician was on the hook for the whole like drywall rip out. And then we got a bunch of human needs, right? Super important part that we sometimes think about, but not always. Right? I think we've talked about this enough, right? How we procure things, how we design things, and how we install things. Codes and standards could be adopted at a municipal level, like Boulder. Could be adopted at a state level, like IECC 2018, I think is what Colorado's on, if I'm not mistaken. 21, thank you. My apologies. And then federal. At this point, I don't know what federal adopted. Standards, right, are the basis usually for codes, but a lot of times they kind of like layer on additional stuff. Who writes all those things? A lot of people. Hard to keep track. Is this a fire protection thing or is this an NEC thing, right? In lighting design, we have to balance all these things. There is a visual experience to all this stuff when we come into a space. What am I supposed to look at? How am I supposed to know where I'm supposed to go, right? Where is the bathroom in this space, right? Where is the exit? Where are the focal points? Where are the gathering spaces? Light and architecture together influence that stuff a lot. I always think about where's the elevator in this building, because that's where the restrooms are. Okay, which one is this? If I have a layer of light that's kind of uniform and broad. Ambient layer, right? Task is meant to help me perform things. Accent is meant to highlight certain things in the space. Usually on a vertical plane. Depending on the space, you have different focuses, right? Utility, luxury. Interesting combination of words there. If I were to describe this, right, it'd be like there's a nice ambient layer, right, that's coming from somewhere. I'm not even sure where, right, to give me some visibility and non-tripping hazard. That's kind of like my ambient layer. I've got accent layers here. This is definitely an accent wall. I've got accents going to highlight my space, right? I don't really have a ton of task lighting in this. You might say that there's a floodlight here for some task lighting, but in general, this is not a high task use space. This is an experiential space. Very different in here. I've got tasks I need to accomplish. I like to use really sharp, big knives, right? My last name is Slaughter. Right, I got stuff to do. I need task lighting in this space. That's I can't help it, sorry. Right, kind of different here. I don't have as many tasks, but the mixologists do, right? They've got tasks, but these are accent. This is accent lighting. This is not task lighting. Task lighting is at the bar where they're doing the mixing, right? Where they're doing the pouring. Everything must be in balance, right? Everything in moderation. That's how you tank array. There's been a lot of talk about sustainability, especially in manufacturing recently, right? Not only in just the materials that we choose to put in architecture, but also as the manufacturing standards sustainable. Like red list is a big deal. Like, are you devoid of all these, toxic plastics, forever chemicals, all that other stuff, right? And there's a whole bunch of different term I'm looking for here is movements and standards, and these are not really standards, right? But they're kind of goals and initiatives of like what we can do, right? Try to make our world a better place. It's not wrong to use these luminaires, which will create uplight into the sky, right? We just need to be considerate about what we're doing. Does it serve the needs? Is it really necessary? Right. Here's 5 principles. Use it where I need it. Make it useful in general sense. Don't use more light than I need. Control it where I can. And use other temperatures to render things well, and create a nice environment. Any questions so far? No questions. Here's some resources. IES has a whole bunch of design guides. They've got a whole bunch of other stuff. CIE is the French version, different entities, but they got a whole bunch of stuff in French.
French?
In French, yeah, the CIE is French. So the IES is the North America side, and these are not the same organization, right? It's just kind of like the French did a lot of work on this early, and the IES on the North American market picked up a lot of the stuff there.
So I've got a French. It's like a confirmation email.
I don't know.
I think one of the confirmation.
You should check your AI assistant on that one. We're here. Right, there's a whole bunch of stuff
You know, some of it's paywall, some of it's free. This was called the lighting certified exam. And the CLD is certified lighting designer exam. And then we talked about topic specific stuff as well. International Commission on Illumination, CIE. That's obviously the English interpretation. Whole bunch of organizations. International Day of Light. I don't know when that is. That's it. Got it. Thank you all once again for I know it's a Saturday, but we're out of here over an hour early, so hopefully that is good. Sorry it took Luminaire so long. I love the questions in general. And you guys are wonderful to meet and be able to talk to you, and thank you for all your engagement. Do you have any other questions? I will also stay around if you have. We were going to talk about something with something. I don't remember what it was. Parspec question. Yeah, unrelated. Cool. Well, you guys have a wonderful day. I'm gonna try to go see what my son destroyed. And yeah, have a wonderful day. Thanks. Most welcome.
Thanks, Chris. Chris, you said you were about startups now? What is your startup?
It's called Parspec.
Okay.
For the lighting industry, we do like a lot of submittals tools, like so people can like build submittals really easily. So we track a bunch of manufacturer websites and catalog all their data sheets so that like people can grab them and don't have to continually go back to it over and over again. So I'm a product manager there, so I manage the software. My background's in software and lighting, so it was a great opportunity, and I think that the tools that like reps and stuff, and like they're crappy. So this was an opportunity to try to make it better. What's that? Sorry.
I think you get to put it all together.
Put it all together and work